Okay, while we're waiting for the arrival of the other speakers, we have 10 minutes, and I would like to share with you and inform you about some news or possible news. So the first point, can you see my slides?
No.
No?
I think you should share.
Yes, yes, share again, yes, okay. Maybe you can see now?
Yes, we do.
Okay, so the first point I would like to share with you is, of course, the current agenda. Essentially, we will move from radio frequencies by going to microwaves, millimetric wavelengths, and then to go towards higher frequencies. The idea is that I'll be introducing some cosmological topics related with the radio background, radio astrophysics, in the talk by Amanda and by Third. Third will focus in particular on the 21 centimeter line that is already discussed during the plenary session by Felix Mirabel. Then we move to the microwaves domain, and in particular, we have a presentation by Marcos regarding the status of the Planck-Leclerc archive and the future for some perspective in this direction. And Elia will present some new types of observation, high resolution with a facility which is Mistral, that is particularly relevant for the Sunyaev-Delbovich effect that has been already well studied with Planck. Then we move towards some specific topics in Planck maps. One is presented by Hideki. Will regard the idea of studying the global maps by induced by Sunyaev-Delbovich, the thermal Sunyaev-Delbovich effect on the sky, and to derive the cosmological implication from these types of analysis. And then Raleigh will discuss about the analysis of the CMB maps, particularly from Planck, to derive information about our motion by several types of correlation analysis. This is an important topic in cosmology with a lot of remarkable implication for the cosmological model and other relevant applications. Then we move towards a very interesting topic, which is the possibility that some violation of fundamental symmetry in physics, in particular the Lorentz symmetry, can be seen in the polarization pattern of the CMB, and to understand by Sedgwick what are the perspectives from this type of studies. Another important topics come from the idea that our paradigm, our general paradigm, can be not so well defined, and in particular, Konstantinos will discuss the possibility of a modified version of the gravity in a relativistic approach to solve the problem of the dark matter, and how it can be, in principle, also used to predict the anisotropy pattern of the CMB, which is a particularly relevant topic for our session. Then Mathieu will touch the important topic of the constraints of the tensor to scalar ratio that typically are considered important topics important way to detect the primordial stochastic background of gravitational waves. Up to now, we are not at the detection level, but there are important constraints that come in particular from Planck. And then finally, Laura will discuss the problem of the strong lensing effect that magnify the signal from far galaxies, in particular from submillimeter galaxies, and that can be used for test cosmological model other than for astrophysics. So this is the outline in which we consider the topics goes roughly from lower frequency towards higher frequencies. So I'd like to share with you some piece of information. In particular, I believe that for many of us, but for all people that are interested in this field, we received recently an important message by ESA that the studies for new missions, new CMB missions, following COBE, following WMAP, following Planck, and following LIGHTBIRD, is under consideration very seriously by ESA, and it will be a very good time for preparing new well-designed mission for the CMB, focused also on the spectrum of the cosmic microwave background. That is a topic that is not so advanced since the times of Hyrax. So another communication I would like to give to you is that with Frontiers, Raoul Dutt and I are announced very recently the opening for a research topic, which is advanced in astronomical observation at millimeter and submillimeter wavelengths. And this issue is open soon, and we can receive paper that could be published on Frontiers in Astronomy and Space Sciences with the sector of astronomical instrumentation and cosmology, and Frontiers in Physics with the section of cosmology. If you are interested, your colleague could be interested in joining this issue, please consider this chance. You have here the link to the topic where you can find other information. Another important information, which is tightly related to this conference, is the fact that has been announced by the organizers that also this time we will have the opportunity to publish the proceedings of the conference that will be published online, thanks to the World Scientific Company. And in this case, since the proceedings will be published electronically, we will have not a limitation about the number of papers, of the pages of the paper. So you will be relaxed in this respect when you have to write your contribution, and you will receive certain information in the next times from the organizer and from myself, of course, regarding the preparation and the submission of your contribution. So note that also we have already published the proceedings for Marcel Grossman 14, and the proceedings of Marcel Grossman 15 are currently finalized and will appear soon, so everyone can read them. So I would like to see if there are other people now. I stop to share my sharing. Hi, Jens. And I see other people. Hideki, okay, Hideki, please, could you like to test if your presentation goes smoothly? Please, if you would like to share your screen to start.
Okay, yes, if it's okay, I share my screen. So my presentation on screen now.
Mm-hmm.
Okay, so.
Okay, if you would like to scroll a bit. Okay.
Okay, scroll a bit. Yeah.
Okay, we can see also that pointer. So okay.
Okay, so I stop sharing.
Maybe you may want to put it in full screen mode.
Okay, full screen mode. Wait. Yeah. How it's is this full screen now?
Yes. Perfect.
Okay. Yes. So wait. Okay, now I stop sharing.
Thank you very much.
Thank you.
Great. Hi, Nabila.
Hello.
Hello. Okay. So I think that we are approaching the time for starting, and so we wait 2 minutes. So I share my screen again, and in 1 minute, we will start with the talk by Amanda, and then by Third, and then we proceed with microwaves. Sunyaev-Dobich effect, select a topic on the CMB, B-mode, tensor to scalar ratio, polarization, modification of gravitational theory, and the strong lensing effect for proving cosmology. So I think that now we can start. So I close my sharing and I invite Amanda to start a presentation.
Great. Just see. Is it sharing fine?
Yes, you can.
Okay, great.
Full screen. Great. Okay.
Great. So first of all, thank you so much for inviting me to join the session. I'm very happy to be here. I'm hoping to tell you a bit today about a couple of different ways that we can probe cosmology using different radio astrophysics projects. So in terms of a very quick introduction, I'm sure that the audience is quite aware. Sorry, I'm trying to make you all invisible, which is impossible. I'm sure you're all aware of the many problems we have in cosmology today, and also the great success that we have, in the sense that we have greater precision of all of our parameters, and we're able to see the anisotropies in the CMB at far greater level of accuracy. So if I look on the left-hand side, if you look at that plot that's showing you us looking backwards in time, you can see that we get so much of our data from very close information, so galaxies that are very close to us, and very far information, the CMB. That region in between is relatively unexplored, and that's part of what we'll be talking about today, and the importance of really getting more information from the full cosmological volume. So in terms of the open problems in cosmology, I think there are several. The obvious ones for many years have been dark energy, dark matter, and inflation, but there are many others. One of which is the issue of missing baryons. So even once we account for dark matter and dark energy, there are fewer baryons than we expect when we add them all up, and there are possible solutions. I think this problem is now basically solved. I'll talk about that as we go. And perhaps the problem that's sort of gathered the most attention in the last couple of years has been the drift of the Hubble constant away from uniformity. So in the beginning, you know, when I started my PhD, I remember everyone saying the Hubble constant was somewhere between 50 and 100, but we were converging on 70. And all the data looked like it was squeezing towards a central value of 70, you can see on the plot there. But over time, obviously the constant hasn't changed on these timescales. It's that the more precision we have in our measurements, the smaller the error bars are, and they don't fit in with each other. So there's this sort of great problem of cosmology having moved from this era of philosophy to precision, and now this precision has actually driven the crisis. So I've included here, you may have seen these plots before. It's basically just showing how many different sets of data, some are from recent times, some are from very far away, but the two ranges don't fit within each other. So if we look all the way back to the CMB, we have this narrow possible range of lowish H0, and if we look at more sort of recent building up distance ladders with Cepheids, we get a slightly wider range, but it still does, the two ranges don't include each other. So it's a real problem. Amongst other problems in cosmology, this is just one of them, and we need a different kind of solution. So different approaches, possibly new theories, possibly entirely new physics, possibly that there is nothing wrong with the existing data, we just have misunderstood it. So our analysis is incorrect, the methods of gathering the data is incorrect, something within there is incorrect. It's possible that if we do build a new theory, we can't just go and explain the existing data. We need to test against new data, so we need new predictions. And in all approaches that we take, we need a range of probes. So we need to really directly and indirectly test our theories. And so that's sort of the argument that I'm making here when I say we should really look to radio astrophysics as a possible region for a sort of rich amount of new information. So the talk that follows me, I think, will probably expand very much on this. So I won't belabor it, but this is the point I was trying to make earlier, which is that we get a lot of information from very early universe, high redshift, and a lot of information from the recent universe, redshift up to redshift 1. And everything in between, we actually haven't as deeply explored as we could. And that's, I think, the next sort of frontier that's coming. 21 centimeter intensity mapping is going to hopefully change a lot of the sort of face of cosmology, but there are other intensity lines that can be probed as well. And I've just included this nice plot from a talk of Eli Kovets, where he explains each of the different intensity mapping experiments, and Hyrax is the one I'm involved in. So I'll talk about that today. So if you don't know what intensity mapping is, essentially you are trying to measure the baryon acoustic oscillations, so the very early time oscillations, by looking at the intensity of the H1 line, basically. So you have over densities in pairs of galaxies at a fixed length of 150 megaparsecs. And if you can track those lines, it gives you if you can track those over densities, it gives you the expansion rate of the universe. Instead of looking at a few galaxies and seeing where they are, and seeing like perfect points of where they are, we sort of look at an overall intensity. And so that's why the use of the pointillist artwork here, because as instead of having to resolve and zoom in to actually see that it's a lady with a hat, we're able to know exactly what's happening in the image from very far away. We get a lot of information without having to use up so much computing time with perfect resolution. So Hyrax is an experiment that's currently under construction in South Africa and ultimately probably also in the rest of Africa. The idea here is to have 6-meter parabolic dishes, 1,024 of them in a regular array with outriggers quite far apart and far away. But the regular array is a very, very simple design. They point all in one direction. You get strips of the sky at any given time as the Earth is moving. And so we're able to, the range that is optimal is between 400 and 800 megahertz, which for intensity mapping is ideal. That gives you a redshift range of 0.8 to 2.5. So that's where you see dark energy or curvature could really be playing a role. And so it's where you get these, you're supposed to get these excellent constraints on cosmology if we're able to control foregrounds properly. On the other hand, that 400 to 800 megahertz range is also perfect for finding transients. So we can find pulsars and fast radio bursts by looking into the sky. And the cosmology experiment is a long, slow experiment where you take all the data and after many months analyze it. The transients experiment is very quick. So as you see one of them, you're able to immediately get the data, communicate with nearby telescopes, and see what's happening immediately. And so it's sort of worth talking about the power of what we can do with fast radio bursts, even for cosmology. And so that's really my main agenda here. So the Hyrax experiment will go, that on the bottom left-hand side is just the simulation of what it should look like. It'll go on the same site as where Meerkat is and where the SKA is being built. So if you didn't know already, Meerkat is just more of CAT. CAT is the Karoo Array Telescope, and meerkats are the animals that live in the desert near where the telescope is being built. Hyraxes live near them, hence the name Hyrax. It seems to be an astronomy tradition to creatively name your experiments. So in terms of what we can do for cosmology, there's quite a lot. My priority has been to constrain dark energy and curvature relative to each other. So breaking the degeneracy between them and figuring out how to constrain curvature. But there's quite a big improvement that we should be able to make. And these forecasts apply in some sense to any intensity mapping type experiment. Now, in terms of fast radio bursts, what are they? Well, we're not really certain, although we have very strong hints now. They were first discovered in 2007, and there were very, very few of them in the beginning. It went from being a few fast radio bursts to hundreds over just a couple of years, maybe a decade. So when I started working on them, we made, a group of my students and myself made this Frb Theory Catalogue, which was 2018. So we built a catalog of all the known theories that could possibly explain them. There were, I think, 48 or 51, and we had more theories than there was data at that point. So there were less than 48 known FRBs in 2018, and now there are several hundred. The major difference is that they were originally found by looking in archival data. So it was changed the way that people were looking at the data because they're very rapid, right? They're millisecond or microsecond length pulses that if you don't have the right time resolution for your telescope, you would just miss them. So by changing the resolution, suddenly these were observed. And then when people went back and looked closely in the data, they found a bunch of them. There was no purpose-built experiments. Now there are. So since CHIME is a purpose-built experiment, they're finding hundreds of fast radio bursts, and they're publishing catalogs of them and also showing that you can cross-correlate them with the rest of the sky, which will be very important for cosmology down the road. So we don't yet really know what physically drives them, though we've seen them coincident with magnetars, so they do seem to be driven by magnetars. We've also seen them in environments that are not really possible for magnetars, so it's very likely that there's multiple classes of them, especially as some appear to repeat, meaning you see the burst over and over again, but there's no known periodicity in the repetition. So there's sort of hints of what's going on, but it's not clear exactly what the full picture is, which makes it quite an exciting area still. And we expected to see a lot of them in the galaxy, especially because we know we have a bunch of magnetars, and yet the first was only observed last year. So there was this question as to how do you bridge that gap? And that problem has been solved relatively recently. So how can you do cosmology with them? Why would you even think they would be useful? Well, although they're very brief, they're also very bright. And because they travel through the cold plasma between us and their source, they are slowed down by 1 over their frequency squared. And so the amount to which they have been dispersed tells us about the plasma between us and them. So it tells us about the electrons, which essentially tells us about the baryons, right? And so you are able to get cosmological information just from understanding the dispersion measure of the object, from being able to measure it and break it up into the right parts. The fact that they have relatively large dispersion measure tells you already that they come from host galaxies. They're not all within our galaxy. So the original question that we had was, could you do better on curvature constraints? Can you get a low redshift curvature constraint? Which is a huge ask, given that curvature really requires a long redshift picture. But we thought we would see what's possible. And so the dispersion measure can be broken up into all these different components. And you see that you get local contributions and you get cosmological contributions. So the fraction of helium and hydrogen in the environment versus the evolution of the equation of state of dark energy. The next problem is to break off which part is known. That from the Milky Way, we know that part. The part we're trying to find out is the dispersion measure in the cosmology, so that's the intergalactic medium. And the part that's going to be unknown for some time is the host galaxy contribution. So if we can get them very far away, the host plays a smaller role. So of course, the higher redshift objects are going to be more valuable. And it turns out, not surprisingly, that the best constraints you can get are on Omega Baryon, because it is Omega Baryon that you're probing, and that the constraints require priors. So they're orthogonal, at least to Planck, but they require some kind of priors to get a reasonably good constraint. But your best bet there is Omega Baryon. On the other hand, if you realize that the FIGM, the fraction of baryons in the intergalactic medium, is not actually a known. We put that as a known number based on what you find in the research. If you in the literature, if you realize that that's actually not well known, and that is because of the so-called missing baryon problem, the fact that 30% of the baryons appear to be missing, we assume they're in the warm-hot intergalactic medium, but we don't know. And you use that as a free parameter and then constrain everything, assuming cosmology, then you could constrain that FIGM and solve this missing baryon problem. So we sort of made this realization just from stumbling our way through the field. And within, so this was, I think, 2018, 2019, within a year, the data was there. So I've never really worked in such a fast moving field, but essentially what this paper does, was first authored by JP McCart. It was his last paper before he died last year. And essentially they found that using, 4 very well localized galaxies, very well localized FRBs within host galaxies, they could show by the differential rate at which the different frequency components are slowed down, they could probe that missing matter exactly. And so that missing baryon problem was entirely resolved in a very short time frame. So there's a lot that you can still do with cosmology. There's implications for the early universe in terms of probing the epoch of helium reionization, not just hydrogen. There's implications for the late universe, a lot you can do with dark energy or dark matter. Dark matter could cause lensing, so you could see strange signals. It requires understanding the data a lot better. There's a lot you can do on intermediate scales. You could understand magnetic fields. And so for sort of cosmology, there's really a huge amount available as we get more data. Even on the level of sort of pure fundamental physics questions, does the photon have mass? You can get a constraint on that based on how much data you can get from the dispersion that you would get if the photon didn't have mass. So there's a huge amount of cosmology that can be done. It's key to really well localize them. And this is a fundamental focus of the Hyrax experiment, which is to build these outriggers across Africa. So it's as if you have a telescope the size of Africa as opposed to just the size of the main array. And then instead of getting arc-minute resolution, we get sub-arc-second resolution. And so we can understand far better the host environment as well as remove any uncertainties from the host. I didn't feel it would be complete not to mention the SKA, because the SKA will do a huge amount for cosmology using radioastrophysics, but of course it's as big as the experiment is, it's too big for this topic. So just to finish on time and make Carlo happy for the rest of the session, I just conclude with lessons that can be taken away from FRBs. And the most important one, I think, is that the discovery of them was not because of some technological innovation, but because of an attitude shift to look at existing data. The technological innovation is needed to get vast numbers and to do more physics with them. But just a change in the way we looked at existing data changed our potential to make really great discoveries. So I think I'll leave it there and finish on time.
Thank you. Thank you very much, Amanda. So if there are some questions, please unmute freely your phones and ask to Amanda.
It was all too clear.
Questions? I have a question concerning your experiment you are projecting now. How much fraction of the sky do you plan to observe along the years?
Oh, you mean over the whole time?
Yes, depending.
Yeah, so we only see sort of one sort of narrow strip at a time, but in principle it should go and we should be able to see large parts of the southern sky. I don't know the exact square degrees that's projected over time. I suppose it'll depend how long it runs. I'm not sure. It's a good question.
Mm-hmm. Okay.
I think Hideki has a hand up.
Yes, maybe just a basic question. Chimes recently released the catalog of FRB. Compared to this, what's the advantage of Hyrax? Can you remind me?
Yeah, it's a good question. So Hyrax has a few advantages. One of them is that we see a completely different part of the sky. So we see the southern hemisphere, whereas they only see the northern. Okay. So we will see different bursts. Another is that Hyrax Chime is limited by the fact that they have snow. So the design of their telescopes is these long open cylinders, like cut cylinders, because if they had parabolic dishes, the snow would just collect. Whereas with the cylinders, they can move the snow off. And so they have a non-optimal, you can imagine that when the telescopes talk to each other, there's a lot of edge effects. And so the cylinder is not as optimal as a parabola would be. And so they have a greater obstacle in that sense. We're looking in the same range of frequency, the same frequency band, but that makes a huge difference. The other big advantage we have is we can communicate to Hera, which takes far wider frequency data. So they should be, if we tell them that there's a burst, they can immediately look and see other parts of the frequency range. And I think the last key point is that we plan to build these outriggers, which now I think actually many of the telescope arrays will do. But we were sort of the first ones to talk about it in some sense because Africa is so easy. You have such a lot of land and gaps to be able to do it. So, and that makes a huge difference. If you want to localize them, outriggers is very important. I think CHIME now have the funding to do that as well. So they will get there eventually too.
Okay, thank you.
Okay, thank you, Amanda. And
by Jens, I don't know.
some questions?
Probably to tighten the program already. Sorry.
Carlo is the master.
Okay. Maybe we can move other questions to the 15 minutes we have back at the end in order to be safe with the talk of Laura. Okay. So now we move to the talk by Firth.
Hi, Carla, I guess you can see my screen?
Yes, I think yes.
Perfect.
Yes, great.
Oh, okay, so let me start. So let me start by thanking Carlo for organizing this very interesting session and also giving me an opportunity to talk about the 21 centimeter line in radios and how to use it to study the high redshift universe. So before going into the 21 centimeter line, let's just quickly recap the history of neutral hydrogen, H1, in our universe. And this is a nice diagram which shows the history of the universe starting from very early times to where we are today. So the universe is expanding and cooling along this direction. And the H1, if you think about it, forms at the last scattering surface of the last scattering epoch. That's also the epoch from where the CMB originates. And then we enter a phase which is very fancily called the dark ages. This is dark because there are no luminous sources in the universe. It's all, no galaxies, no stars, they're all yet to be formed. But there is a lot of hydrogen there sitting, and gravitational instability is slowly moving forward and eventually going to form galaxies and other structures. And that happens somewhere around, we think, I mean, we don't know the exact redshift, it could be somewhere around 20 or so, when the first luminous sources or the first stars in the universe form. This phase of the universe is again popularly known as the cosmic dawn. A very important phase of the universe, and there's a lot of effort being spent in trying to study these epochs. And then we enter a phase which is known as Epoch of Reionization. This is the phase where the neutral hydrogen is getting destroyed by ionizing photons, the UV ionizing photons coming out from these stars which we have formed. And this is a very complex process and has a lot of information about the early universe, I mean, so-called the high redshift universe. And we believe now that this would have ended somewhere around redshift 6, maybe somewhere around redshift 5.5. Things are becoming clearer as days progress. And then we enter a regime which is known as the post-reionization epoch. So in this epoch, the neutral hydrogen can only be seen in high density regions like galaxies, because these are the places which can self-shield themselves from the ionizing radiation. The so-called diffuse intergalactic medium is highly, highly ionized. So that's where we live. We live in a very ionized universe. And of course, this is a picture, this is a story I told. And the pieces of the stories have been built like brick by brick through very many different experiments which have contributed to the story, coupled with a lot of theoretical modeling, calculations, and so on. So of course, we won't go into all these details, but this is just to give you an idea about how rich this field has become over like last 1 or 2 decades. Of course, what I wanted to focus in this talk is looking into kind of future, it's probably happening now, but it will happen a lot in the future, is to study this neutral hydrogen using the 21 centimeter line. And of course, the 21 centimeter line, we all know, originates because of the spin flip of the electron with respect to the proton, and clearly traces the amount of neutral hydrogen as well as properties of the neutral hydrogen distribution. So that's the power. And the basic idea, the way one is planning to detect this line, is to use the H1, the neutral hydrogen, as, I mean, something which, rather use the CMB as a background in front of which the H1 sits and does something to the CMB photons. And that's something we plan to observe. Basically, the departure from the CMB, or in other words, the distortions in the CMB spectra. So the idea is the CMB photons are traveling from the high redshift, the last scattering surface, to us. And in between, if they encounter neutral hydrogen at some given redshift, and if the redshifted frequencies of these CMB photons match the 21 centimeter, the frequency corresponding to the 21 centimeter line, then there could be interactions. And depending on what the state of neutral hydrogen is, it can either absorb the CMB photons or add to the CMB photons. So we will observe this signal either in emission or in absorption. And which one will be dominant will depend on what we call the basically the level population between the two levels, because we are looking at a two-spin system which has a triplet and a singlet state. And this level population is usually characterized by what we call the spin temperature. So what we will observe is a signal which will be essentially proportional to the amount of neutral hydrogen present. And how different is the spin temperature from the background CMB temperature in this case? Now you can ask, what does the spin temperature depend on? The spin temperature, again, depending on the conditions, will either tend to couple to the CMB temperature. In that case, there won't be any signal, or it can couple to the gas temperature. And if the gas temperature is very different from the CMB temperature, there will be a signal here. And you can see this term can either be positive or negative. And that's basically absorption or emission. Now, if I have to quickly summarize the various observational plans for detecting the 21 centimeter signal, let me start by saying that there are broadly two kinds of experiments which are going on and are being planned. One is to detect this signal as a globally averaged quantity. Okay, so you will be getting this signal average over large volumes of the sky. So you can think of that as a global signal. That will be like one number, so to speak, per frequency, which actually corresponds to one number, one value per redshift. Okay, so this is why I call it global. And then you can also work with the fluctuations. Okay, of course, the fluctuations will have much more information in some sense compared to the global. Now, currently, of course, there is a lot of being planned, but currently I can say that the global experiments are broadly concentrating on the cosmic dawn and the epoch of reionization part. And you can, if you want to get a feel for what frequencies they correspond to, it's given here. And there are many experiments, and I have chosen some representative ones. This list is not by any means exhaustive. So there is this famous edges signal, which I will talk about briefly soon. There is SARS-2, which is also taking data, and I guess they have analyzed a big part of their data. There is LEDA and so on. If you go to fluctuations, what you will realize is most of these experiments, the global experiments, are done by very simple kind of instruments. I mean, they are very small, easy to carry kind of a thing. Whereas fluctuations are usually you have to go to interferometric arrays or big telescopes. And again, in fluctuations, one is of course targeting cosmic dawn and epoch of reionization, but you can also look at post-reionization, the era after reionization is over, where neutral hydrogen is only within galaxies, using fluctuations. And this is the part which I think the previous speaker also talked about. This is where the intensity mapping concepts come into the picture. Again, there's a lot of experiments which are going on in trying to detect these signals, starting from MWA to LOFA to GMRT, which did some detections, put some upper limits at very initial stages. And of course, we talked about CHIME and then Meerkat. Again, by no means exhaustive, but some representative ones. Of course, I won't have time to discuss everything in this talk. So I've just chosen 2 of the topics which I like. That's the cosmic dawn using global experiments and epoch of reionization using fluctuations. So the global 21 centimeter signal, when plotted as a function of redshift or as a function of frequency, shows a very rich structure. So what has been plotted here is the temperature, the brightness temperature, and you should think of this as a brightness temperature with respect to the CMB. So a 0 means basically you're observing something which is consistent with the CMB. Now, and this signal does various things, and we understand what's going on. Of course, this is coming from a model. I mean, we haven't yet detected this signal in that much glory. But you can clearly see there is one part of the signal which shows a very prominent absorption feature. Okay, it goes negative, so you have less photons than the CMB. And this essentially is happening when the first galaxies in the universe form, or the first stars in the universe form. And the physics is again very nice here. It has to do with the Lyman alpha photons from this galaxy coupling the spin temperature to the gas temperature. And now since the gas is cold, you see it in absorption. But at some point, the same galaxies will throw away X-rays and that will heat up the medium. So the moment the heating starts, this thing, the temperature tends to rise once more. So hence you see this. And this is what most of the global 21 centimeter experiments were targeting to detect, because that is the most prominent signal. And that is where Edges came up with their result. It's almost 3 years back now. And you can see this is what they have detected. Of course, the detection, I mean, there are a lot of controversies also regarding the detection. It's not clear whether it has to do with not very good foreground subtraction or some other systematics which have crept in. So I won't be going into the veracity of the signal, but nevertheless, the signal, what it did was its amplitude turned out to be much larger than what is expected from standard models of first stars and reionization. Now, what happens is if you want to produce such a large signal compared to the standard models, what you have to do is you have to make this part, the difference between the spin temperature and the CMB temperature, large. And the way to do it is to either decrease the spin temperature. For that, you have to make the gas colder. Now, we know there are a lot of astrophysical effects which can heat up the gas, but we don't know anything which will make the gas cooler. So that's why this led to speculations that the gas might be interacting with dark matter, which is cold and so on. Or the other option is you say that there is more radiation compared to CMB at those wavelengths. So in other words, there is a radio background which has been set by the first stars. And this is something we also tried to play. So this is some work which we have been doing after these data came out. Where we actually ask the question that what kind of stars you need to match the data. I mean, it's not really a forward modeling, but you ask the question in a reverse way. So of course we can fit the data because that is what we are looking for. But for that we need some stars which have this kind of star formation rate. So they are born somewhere around redshift of 20 or so, but they have to die. And these are what we think are the metal-free POP3 stars, which probably gave rise to the signal if this is confirmed. But we do also see is that those stars need to have a very strong radio background, stronger than anything we know in the local universe. And there is no good explanation for that radio background. We just know that we need it, but we don't have a really self-consistent model to describe this. So one has to really wait for the other telescopes to come up and prove or disprove the presence of this signal. If we now go to the epoch of reionization, there the fluctuations are very interesting. So what I have shown here is this one is basically a plot of the density field. And as you know, I mean, as as time progresses, basically this cosmic web forms. And by these white points, I try to show the formation, the presence of the galaxies. And you can see the galaxies will basically trace the large scale structure. On the right hand side, I show the neutral hydrogen map. And you will see that wherever there are galaxies, regions which are of higher density, you will see that regions grow black, basically. Those regions get ionized because of the radiation coming out from the galaxies. And that basically tells us that the neutral hydrogen distribution, the fluctuations in some way know about the galaxies which ionize them. And that is how this game is going to be played. We try to detect the neutral hydrogen, the fluctuations in them, do some statistics, and through that try to learn about the first galaxies. And the statistics, when you try to do fluctuation, the first statistics which come to mind are the power spectrum. So what I have shown here is for that reionization model, I show the power spectrum as a function of k, of course, and you can see as reionization progresses, this power spectrum does various things. It goes up, comes down, the peak, the position of these peak shifts, and so on. So these have all to do with how reionization progresses, how these individual bubbles grow, overlap, and so on. And suppose I just fix at a scale, let's say k equal to 0.1 h by mpc. At that scale, the power spectrum as a function of redshift or frequency will behave something like this. Okay? It goes down, and then there is a clear peak somewhere around redshift of 7, and that corresponds to the place where universe was like 50% ionized. So this patchiness really shows up in the power spectrum. You can also maybe look at the values one is typically talking about. One is talking about few to tens of millikelvin square, because since this is the power spectrum, so that's the amplitude. And you can ask, where are we now? We are somewhere here. So these are various data points at plotted at k equal to 0.1 h by mpc as a function of redshift. And most of the experiments are here, and the field is essentially driven by LOFAR and MWA. So their upper limits are somewhere here. And one expects that with something like 1,000 hours of data, with these telescopes, one will reach a level which is somewhere here. It's still not there to really starting to rule out or constrain reionization models, but we may be able to rule out extreme ones. And with SK, the field will be revolutionized, as one knows. And so this is looking into the future where SK low comes up. And also there are other experiments planned like Hera in South Africa, which will also, their target is to detect the epoch of reionization. I had one slide on CMB because I understand there's a lot of interest in CMB in this audience. So basically reionization also plays a role on the CMB can play a role in understanding reionization because of the CMB photons getting scattered off free electrons. And there are a lot of effects to play with. And there's a lot of work various groups have done, including us, where we also, for example, tried to look into the B mode signal, which will be generated because of patchy reionization, and whether it can play a spoil sport in the primordial B modes. And while doing our analysis, although I won't go into the details of the results, we realized that it's already possible to put a lot of constraints on reionization using only CMB data. Forget about anything else. So for example, Planck and SPT, which gave us the KZ signal in recent times. Of course, with next generation of CMB telescopes, I mean, this will also play a big role in constraining reionization, and we'll probably have a much fuller picture. So that brings me to the summary slide. As I said, the 21 centimeter observations would open a new window in studying the high redshift universe. So we have some possible detection of the global signal, but it's not clear whether it's true, but there is already interesting results on the fluctuations coming from MW and LOFAR. There's a lot of scope for theorists like me because one needs really accurate and efficient models to interpret the upcoming observations. So let me stop here. Thank you very much for your attention.
Thank you, Peter. We have time just for one question, please. Please unmute freely.
Jens has a question.
Yeah. Thanks for this nice talk. When you were modeling the basically enhancement of the radio background to explain the edges result, it was my impression you were modeling it specifically to basically have the enhancement around the line to even mimic line shape, but it's also conceivable that it's just a more broad radio background which is enhanced and maybe a connection even with the arcade measurement. Have you explored those models more
Yes.
broadly, or what is the conclusions on that?
Yes. So what happens is, so what we do is we say that this population 3 stars, this transient population, are the drivers of the radio background. So what happens is, what I'm showing here is the production of the radio background. So they will just follow the population of of these stars. But of course, the radio background doesn't die away. I mean, the stars die away, but the radio background remains. And we then extrapolate it, for example, to lower redshifts and try to see, I mean, how does it match with arcade excess and so on. So we should be, I mean, because they die down, so there is no production of a large radio background afterwards, at least from these stars. There is no problem in satisfying the arcade limits, but we haven't looked into like more detailed physical models of how this radio background is produced and what their implications are.
Okay, thanks, Bert. We move to the talk by Marcos.
Yes. Okay, just a moment. Okay, can you see my screen?
Yes, we can.
Okay, so let me start. So good afternoon. My name is Marcos Robertaniego. I'm an astronomer working at the ISAC Science Data Center near Madrid. And I would like to thank Carlo and the organizers for inviting me to tell you a bit about the Planck Legacy Archive, the present and the future. I've seen many old Planck friends in the list of attendees, but there are also some other people that I don't know. So maybe there is something for them in the Planck Archive to do their science. So let me start. The Planck Legacy Archive, or PLA, currently hosts over 200 terabytes of products from the Planck mission. We host a very wide variety of products, from cosmology products, frequency maps, catalogs, and you will see it in a minute. So when you enter the Planck Legacy Archive, you will see that you have direct access to the Planck main product categories like maps, catalogs, cosmology projects, and time order data. Then we also have the Planck Sky simulation model, an interface for that software, as I will talk a bit more later. And then we also have direct links to the Planck explanatory supplement and the collaboration papers and some other pages from the Planck science team, and very important, to our help desk, so where you can contact us and ask for questions or give us comments and feedback. So in terms of maps, we have a very large section of maps, and what I'm highlighting here is that so Planck has 4 data releases. It's the PR1 in 2013, the PR2 in 2015, PR3 in 2018, and more recently the PR4 in 2020. And then there is, but in general, you will see these checkboxes showing by default the so-called legacy products, which is a selection of products from the PR1, PR2, and PR3, which are the ones that are more easily accessible, let's say. Then also throughout the archive interface, users can find these direct links to the explanatory supplement for the relevant sections. And then, as I was saying before, we have the over 150 papers of describing the Planck products and the science that has been done with them. We have I will not go into the various subsections of maps. We have the frequency, CMB, foreground, correction maps, mask, very important. And we have a section on simulations that is really important, And so we received some questions in the helpdesk because sometimes people don't find the large and really extensive set of simulations that we host in the PLA. This is because here in the main, in this part of the interface, what we have is the, let's say, the realization zero for these simulations. But then if the users go to the advanced search, in particular to the simulated search area, users will be able to find the whole set of simulated data. Then it's also important to mention that since we have the full set of Planck products, we have covering not only the nominal mission, but also the very different periods of the mission. And so sometimes it's difficult to find things because the products are very different, and then you need to know a bit exactly what you are looking for. So this is how the interface looks. For example, when you search for a 30 GHz map, and then you see the results for the various releases from PR1 through PR4. Then in the archive we have these links that allow users to send these maps to external software via the SAM protocol, for example, to Aladdin. And since the Planck maps in their headers, they have the necessary polarization information. It is also possible to use Aladdin to display the polarization orientations. Then we also embedded in the archive, we have this Aladdin Light-based views, interactive views of the maps that you can zoom in and zoom out, a bit like in Google Earth, so that you can navigate the Planck data in a visual way. Then also in the results panel for the maths product, we have this icon that essentially gives users the possibility to make all kinds of different operations. So not only to make cutouts in small regions of the sky or in full maps, we have the possibility to do component subtraction of the various components that we have in the archive, unit conversion, and other more complex operations that are useful for some people, like bandpass transformations and color corrections and masking. Then in terms of catalogs, so we have all the catalogs that have been produced by the Planck collaboration. The most recent ones are the BIP catalog, which is a Bayesian reprocessing of the second Planck catalog of compact sources at 857 GHz. And the PCNT is the Planck multi-frequency catalog of non-thermal sources. Similarly, we have the possibility to send these catalogs into a SAMP-enabled software, like in this case, like TopCat. And for cosmology, we have a very extensive section on the cosmology products. Then for timelines, time-order data, and then we have not only the possibility to search for timelines and for rings, which is a type of compressed timeline product, but also we have the possibility to make maps out of them and cut them in time and in space. And this is also a very nice functionality that allows to do extra new science with the Planck time-order data that has been used in a very specific way when producing the Planck maps to do the oriented more for cosmology, let's say. Then, as I mentioned before, we have an interface for the Planck Sky model. So this is a software that was developed by Jacques Delabrille and collaborators within the Planck collaboration. And then what we made is a, let's say, somewhat simple interface for a very complex software that is very powerful and really allows to simulate the CMB and the SC emission and galactic emission and point sources and far infrared background at various wavelengths in temperature and in polarization. And we provide different Planck cosmologies, but this software can also be used not only for Planck to simulate Planck channels, but also it can be used to simulate new experiments and to simulate custom instruments and providing the instrument characteristics, so that starting from a pre-simulated sky, it is very easy to observe this sky with these custom instruments. So we think this is very useful for people working on future missions or current experiments now that are not necessarily Planck. Then we have another section on software, beams, and instrument model that is very useful for people using the Planck data. And then I also wanted to mention that a selection of the Planck products is also available in this tool called LISA Sky that is available in this URL sky.isa.int. This is a visualization platform that has been developed here at ISAC in Madrid that is sitting on top of the astronomy archives and allows to navigate across wavelengths for very different missions, not only ESA missions, but also for missions from NASA, JAXA, and the Chinese Academy of Sciences. And then it's possible to overlay Planck catalogs and maps and see them together with data from other experiments. And then I also wanted to tell you about this new platform that is called ISA Data Labs. It's a scientific research platform. We are developing it at the moment, and it will be open and publicly available later in the year. And then this will also allow users to analyze and explore Planck data without having to download anything. Because Data Labs is it's a science exploitation platform based on Jupyter Hub with virtual machines. We'll have some shared and private storage area, decent computing resources, and pre-mounted access to the Planck data and pre-installed libraries to work with it. So it will also be a place to develop pipelines and to test them and to execute them in production, at least for some ESA missions. And it's also a collaborative and inclusive research area because it will be a place to share code and results with colleagues, and it will also allow to lower the access barrier to archival data and computing resources to less privileged astronomers. So as I was saying, stay tuned because we will be opening this platform very soon. And this is just some screenshots of how this platform will look like. So for the future additions to the Planck archive, so we continue with the release of the Planck PR4 products. So we already released the frequency maps and the CMB maps, and now we are working on the release of the simulated data and time-ordered data. We are also planning to keep updating the Planck Sky Model software with the new software releases that are become available. Also, in the future, we would like to add products coming from the projects funded by the European Union, like the H2020 calls. In particular, we are already in discussions with the Beyond Planck project and radio programs, and a selection of products from these projects will be also included in the Planck archive because it will complement very well the current mission products. In the particular case of Beyond Planck, we are also considering the possibility of having a specific area in ISA Data Labs to do for some further analysis with the products from Beyond Planck. And then we are also open to include other higher level products that use Planck data in some way, in one way or another, and that add value to the archive. And for this, if you would like to make such additions, then you will need to contact us through the PLA help desk or contact directly the project scientist, Jan Tauber, with your request, and he will come back to you. And I will stop here and take any questions.
Thank you, Marcos, very much for the presentation, in particular for the new development. And there are questions. We have time for 2 questions, I think, 2 or 3.
Yeah, so there's a question by, okay, there are several questions. So please, Nabila, maybe you want to start?
Hey, hello, Marcos. How are you? Nice to see you. So my question is about the additional data. Sorry if I missed it. So you mentioned additional data from the European H2020 programs and additional data from space missions, etc. Is there any plan for adding some ground-based data experiment, something like with the mimic or mirror what Lambda is doing? In particular, I was thinking of the ground-based CMB experiment data that could be added to this.
Yes, so this was discussed in the past, particularly with some of the experiments that are currently located in the ISC, but it is not restricted to them, of course. But we didn't get to the point of doing any of this. But of course, having the PLA already set up and with all these different tools, it would be a great place to have data from other experiments, not necessarily a full repository from these other experiments, but at the very least, the most relevant products coming from them. So we haven't done anything in that direction yet, just because no one has approached us with really a data set saying, could you please put this in the PLA? but we are definitely open, and this has been discussed with Jan Tauber in the past.
Okay, so it's more like people approaching you than you approaching people, from what I understand.
Well, if I knew if I had the list of people to approach, I would
Okay.
I would definitely. So if you have suggestions, just drop me an email, and then
Okay, fair enough.
and it would be
Thanks a lot. Thank you very much.
Thank you. So
welcome.
Hideki?
Yes, I have a kind of question about Planck sky model. On
Yes.
the legacy archive, is it still a pre-launch version, or already some update from?
No, it was the last version. It was updated like 2 months ago, and it already includes the latest galactic diffuse emission models used in the Planck PR3. So it is really a very recent version of the software.
Ah, okay, thank you. Good.
And also we have Mathieu in the audience, so if you have specific questions, he's been involved in the development, so he may be able also to give you more information. But yes, it's a very recent version of the software.
Thank you. I didn't notice that. Thank you.
I have a question for you, Marcos, regarding the future, or how do you think about this infrastructure can be replicated, can be used also for much more extensive experiments, for example, for the new ESA CMB mission or for light model. So do you think that essentially a very similar platform can be used also in the future, or that the global design needed?
No, I think it can be used because even though maybe you go to the interface and it hasn't changed much for over the years, and we only did some to the outside world, it only looks like some cosmetic changes, but on the back we are always upgrading the technologies behind the archive, and this keeps moving, and then we are connected to very powerful databases, the same databases that deal with the Gaia data or with the Euclid data. So we can definitely handle any new very large mission. It's just a matter of the consortium approaching ESA and requesting something like this, or involving ESA from the beginning in the development of such an archive, like it was done with the Euclid case. Well, of course with the Planck case, but more recently with the Euclid case. So yes, I think it can be done, but it needs to be discussed with Jan Tauber and the relevant people at ESA.
Okay, thank you. Okay, so if there are no other questions, we move to the presentation by Elia.
Hello, everybody. Can I share my screen? Maybe Marcos should stop sharing. Thank you very much.
Sorry.
Can you see my screen?
Yes.
Okay. Hello, everybody. I am Elia Battistelli from Sapienza University, and the topic of my talk is going to be high angular resolution Sunyaev-Zel'dovich effect observation, and in particular the case of Mistral, which is the new camera that we are building in Sapienza for the Sardinia Radio Telescope. Let me also thank Carlo and the other organizer for this kind invitation. So this is an overview of my talk. I will briefly discuss the Sardinia Radio Telescope. I will give you some hints about instrumentation. I don't know, this may not be the right audience, but just to show, what is keeping us awake at night and let us work 95% of our time. And of course, a science case with some particular view of the Sunyaev-Zel'dovich effect, and finally I will end up with conclusions. So the Sardinia Radio Telescope is this beast here. It's a very large telescope, 64-meter primary mirror, started building in 2003 and completed in 2012. The enough people who managed the telescope did some technical commission and astronomical commission up to 2014, and the community started using it in 2016 with an early science program, and then in 2018 they started the regular proposal time. It's located, as the name says, in Sardinia. And it's a very large telescope suited up for observation up to 116 gigahertz, so up to the millimetric, thanks to the surface rough RMS, which is good for this kind of observation. And also there has been an extended site testing, sky opacity or sky opacity monitoring, showing that the opacity at the site 50 kilometers from Cagliari is the opacity is of the order below 0.15, with precipitable water vapor of the order of below 8 millimeters. Just for comparison, this is similar value that you can see in another large telescope that do millimetric observation, the Green Bank telescope. So as said, it's a very large telescope, 64 meters primary mirror with almost 7 meter secondary mirror. It's a Gregorian configuration. The primary mirror is composed of 1,000 elements, electromagnetically controlled by actuator, and also M2 is composed by 49 elements that can be adjustable even during observation for focus operation. Both the primary and the secondary mirror are not perfectly parabolic or hyperbolic or elliptical. They are shaped in order to avoid off-axis radiation. This is the place where we are going to put our Mistral, the Gregorian room, while the top focus is the location where the low frequency below 4 gigahertz receivers are going to be hosted. So as I said, it's a very large telescope, so I just decided to put this picture here in my presentation. This little dot here is myself during a walk on the primary mirror in 2016 when we were doing C-band observation of Andromeda galaxy. So what happens recently? If you had observed with the Sardinero telescope until now, you would be able to observe with an L, P, C, and K band receiver up to 22 gigahertz frequency. In 2018, the ENAF gang, the ENAF people applied for a PON, a European call, for an upgrade, a very big upgrade of the receiver fleets of the Sardinero telescope, and they got this PON. One of these camera is a millimetric camera with multi-feed millimetric camera. So they opened a call of tender, and we participated to it with Sapienza. We got this call of tender, and this is why we are now discussing about Mistral. That is the camera that will be populating the Gregorian focus of the Sardinero telescope. So what is Mistral? Mistral is basically this receiver here, which will be attached to this turret, which is in the Gregorian room. So this turret allows to switch receiver when you need to observe with the Sardinero, with the Mistral or other cameras, and moves in elevation with the primary focus. So Mistral has a lot of limitation, clearly, because it has to move with the cryostat itself. Limitation in terms of weight, limitation in terms of room, RF limitations, but also limitation with the use of pulse tube cryocooler, which are the typical objects that you want to use to cool down these receivers, and that usually work with compressors that cannot be very close to the cryostat. So basically, we had to test the compressor with the use of this cryocooler 120 meters away from this receiver in order to have the compressor not to be tilted during observation. So the cryostat is a cryostat with different shields, a 40 Kelvin shield and a 4 Kelvin shield managed by a 1.5 watt Sumitomo pulse tube cryocooler. The lower sub-Kelvin stages are managed by a helium-10 absorption refrigerator, 1 Kelvin, then a 350 millikelvin, and the 250 millikelvin for the detectors, temperature. The optics was also a quite challenging design. the filters, the quasi-optics, the filters design is a combination of metal mesh filters with thin infrared filters and low pass and band pass filters that finalize the bandwidth at 90 gigahertz plus or minus 10 gigahertz, around 90 gigahertz. And this also is managed by, is being taken care by the QMC instrument in Wales. But also important is the fact that Mistral uses two silicon lenses, this one and this one, to focus the Gregorian focus, which sits on the window of the cryostat, down to the detectors that are far away. The use of this Gaussian telescope, these double lenses, is because we need to refocus, and also because we want to stop stray light from reaching the detector, which would be a real problem in case in case of extra load on the detectors, which will hamper the capability and the sensitivity of the detectors. So this is the design of the optics, just to show the design of the optics performed by Marco De Petris. On-axis signal with the stereo ratio of almost 1, 0.97, and very good performance also at 2 arc minutes aside the axis, which makes the focal plane size in sky 4 arc minutes. Detectors are kinetic inductance detector. They are superconductive detectors. The way they work, they incoming radiation break Cooper pairs that keep the superconductivity. And basically, these detectors, what these breaking in Cooper pair do is they change the response to AC bias of the detectors. Basically, they are very high resonance LC resonator, very high Q LC resonator that change the resonance frequency upon incoming radiation. This change in resonance frequency can be calibrated, and in addition can be tuned to have a slightly different frequency, RF frequency, so that a large array of detector can be biased with only one electronics with the using frequency domain multiplexing. So this is the array of detectors. We are going to host 408 pixels with the Hilbertian third order configuration. They are titanium aluminum bilayer of superconductor, and as I mentioned, the field of view is 4 arc minutes. The full width of maximum is 12 arc second, and the pixel separation is 10.6 arc second. So not exactly Nyquist sampling, but smaller size pixel separation with respect to the angular resolution. And this is the design of the holder, on top of which, of course, we have the band pass filter we're going to use. So, of course, we have done electric monitoring. We are nowadays doing optical monitor of this detector. This optical performance, which depend on the temperature and are of the order of 10 to the minus 16 watt square root of hertz, have to be compared with photon noise coming from the atmosphere and from the optics, which is not a steady noise, so it can fluctuate. Imagine we can have a steady atmosphere. This drives to almost 10 to the minus 16 watts square root of hertz for 30 gigahertz bandwidth, and 0.7 10 to the minus 16. Unfortunately, atmosphere fluctuates. So what we have been done is a toy model that allows to take this, which takes a merit function, a signal to noise between a Sunai-Zeldovich effect signal and the noise we expect in our receiver due to atmospheric fluctuation, and take the two extreme case. In case of totally uncorrelated noise, of course, enlarging the bandwidth, we increase the signal to noise ratio. And the totally correlate noise, of course, enlarging the bandwidth will decrease the signal to noise. This is because when you enlarge the frequency bandwidth, you have the tails of the atmosphere coming in. Of course, the situation sits in the middle, and this is the the green and the red curves, which imply some level of filtering. This level of filter include basically two kinds of filtering. One is the second order polynomial fit of a single scan, tested with real data at lower frequency, and 1 Hertz filtering of the signal. And this can be applied to real scanning strategy, which clearly drives the kind of removal of atmosphere we can adopt. The standard on-the-fly map, which is the one shown here in this graph, radiation or declination scan can be applied. And this is what Sardinian telescope can already do. Or a more advanced DESI scanning with DESI pattern scans over the sky. At the center of this coverage map, we can put any observable, for instance, a galaxy cluster, and we can measure the emission of the galaxy cluster with respect to the surrounding emission. So what we are planning to do with Mistral? Mistral is clearly a facility instrument. These are a list. I don't ask you to read all these science case, but it's a list of very important millimetric observation at 12 arc second, angular resolution we can do with 4 arc minutes goal. I would like to concentrate a little bit on the last point, which is the Sunai-Sedovich effect measurement with high angular resolution. So we can no longer do bulk SZ measurement. We can go into the detail of the galaxy cluster pressure profile and try to detect hot electron outside galaxy cluster. Just, I know it's not needed, but just to summarize what the Sunai-Sedovich effect is, when cosmic microwave background photons interact with hot electrons in galaxy cluster, they undergo inverse Compton scattering. What this inverse Compton scattering does is basically takes the frequency spectrum of the CMB and bumps the spectrum up to higher frequency. So what we are observing is the difference between the red and the blue curve you see here. And this is the spectrum of the Sunai-Sedovich effect, which is a negative signal below 217 gigahertz and a positive signal above 217 gigahertz. So this spectrum is almost a universal profile in terms of frequency spectrum, and the intensity of the spectrum depends only on the Y parameter, which is the electron density times the electron temperature integrated along the line of sight. The same electron that scatter the CMB produce X-ray emission, but with different dependence on the electron density and with the electron temperature. So these different dependence can be used to disentangle the degeneracy of one or the other observable if they have comparable angular resolution. Thank you. So here also I listed some Sunai-Sedovich effect observable we could try to detect. For instance, galaxy clusters are not always relaxed. They interact, they collide, they merge. And so going into the deep of a galaxy cluster, measuring the pressure profile is a real important information for intracluster medium thermodynamics. And this measurement could include the turbulent motions and substructure in galaxy cluster. Even relaxed clusters experience some pressure fluctuation. Measurement of the power spectrum of the pressure is a very important topic. We do not need to assume a pressure profile like the one that we have been using in basically all the experiments. We can measure the pressure profile, and also we can measure the point sources that reside in the field of view we are observing. Again, pressure, temperature, mass profile can be studied, and we can also calibrate the usual Y versus M relation, which is important for cosmology. Galaxy cluster also experience some hierarchical growth through mergers, and when they merge, they dissipate an enormous quantity of energy with turbulence, which we would like to see with not only X-ray observation, but also SZ. All these the science cases are even more important, are very important, and we can see them up to higher distance from the galaxy cluster center, because the Sunyaev-Zel'dovich effect is sensitive to the electron density and not to the square root of the electron density as the X-ray emission is. Last but not least, we may want to go outside galaxy cluster. We have heard about missing baryons. We know that magneto-hydrodynamical simulation predict that the missing baryon reside in cosmic wave filaments between dots which are hosted by galaxy clusters. And these are particularly low density optical conditions that could be very good for Sunyaev-Zel'dovich effect measurement. We would like to see and to map the cosmic web with experiments like Mistral. Just to make you an example, we have already done this observation with another instrument. This is Mustang 2 at the Green Band Telescope. This is a couple of clusters where we mapped only one cluster, Abel 401. The second one is outside the map, and we hope to have seen a filament bridge. We are still analyzing data, so this map is to be considered very preliminary. But just to show that this kind of map can be done with an instrument like Mistral. Just in terms of schedule, this is the schedule. We are now in the phase of fabrication. We will start the integration after summer, in September 2021, and we will start the installation after, with the new year for a couple of months that we will use to validate technically the instrument. Mistral is a facility instrument, so we are open to help. But what is key is that any of you can propose observation to the Italian facility, to Sardinian Telescope facility, for using the Mistral instrument. So I am very happy to give this talk with the hope that this will be real in the next months. So I am out of time, so I leave the conclusion to you. But of course, if there are questions, please. Thank you very much.
Thank you, Elia. We have time for one question. I have a question for you, Elia, regarding the typical maximum sky area that you believe is possible to achieve with Mistral with the good quality of the image.
This is a very good question. So the field of view is 4 arcminutes, so we are sure to be able to recover maps of 4 arcminutes. This is something we are also testing with Mustang 2, for instance, and this map is much larger than 4 arcminutes. This is several, the distance between this cluster and this cluster is 35 arcminutes. This all depends on how efficiently you can remove atmospheric fluctuation. That's why I showed the simulation that we will be doing. Roughly speaking, we can do very large map, but not recovering very large structure. So we can map a large object by seeing only the point sources and small structure. For the large structure to be recovered, this is under test. This is something that is not solved yet, but I feel that we are doing many progress as this map is showing.
Okay, so do you think that in principle also secondary anisotropies could be addressed in terms of CL with Mistral?
Also secondary results?
Yes, the secondary results.
This is an open facility, and there are a lot of science cases that are being addressed with the Mustang, with the LMT, with several observatories that measure a similar frequency and a similar angular resolution, protoplanetary curves, mapping galaxy SID, star forming molecular clouds. There are several, yes.
Okay.
There was a question by Andrea. I don't know if
other questions? Oh, yes, okay.
If there is time, otherwise it's not a problem. But thank you for the nice talk. I was just wondering, it's a pretty technical one, but since you mentioned the Y-M relation regarding Sunyaev-Zel'dovich, I was wondering, what is the lowest bound of masses that you can actually target, since the resolution is very small?
Okay. I should come back to this on this to you. I don't want to say something that I'm not aware. I have to check with other that have done already this simulation. We have this number in hands, but I will come back to you. Sorry.
Okay, thank you very much.
Thank you.
Okay. Thank you, Elia. So we continue with the talk by Hideki about cosmological analysis of Sunyaev-Dovich.
Yes.
Advise, of course, a few minutes in advance.
Okay.
From the end of your talk.
Okay. So is this clear?
Yes.
Okay. So first, thank you for giving me opportunity to talk about my work. I will talk about new Planck SC map and its cosmological analysis. My name is Hideki Tanimura. I'm a postdoc working with Nabila Ghanim and Baryon. Motivation of this study is there is a kind of famous tension in cosmology called sigma S8 tension, and there is a slight tension between Planck CMB measurement and the local weak lensing measurement and the cluster count analysis. And the TSC is very sensitive to S8 parameter, which is a mix of sigma 8 and omega m parameter. So this is very good probe. And another reason is the Planck TSC map has not been updated since 2015, but now there's a good motivation to do it because Planck recently released the PR4 data called end-pipe maps, which have improvement in temperature maps in terms of calibration and the correction of bandpass and more data, etc. So these systematic and statistical improvement allow to construct a better SC map and also will provide an unbiased view to cosmological and astrophysical analysis. Just to remind, SC effect is the distortion of the CMB spectra caused by high energy electron in galaxy clusters. And the SC effect has a characteristic spectral shape. So you can use this shape to extract SC signal called Compton Y parameter. Now, first we constructed the SC map with 10 arc minutes and also Milka algorithm, which is in the same as the old one. And we compare the maps. So left one is the new one we made, and the right one is the old one. You see improvement in the up looking. In the new Y map, level of survey stripe pattern is significantly reduced. This is because in the frequency map it's suppressed, and this improvement propagates to the new SC map. And in more detail, we compare in the histogram. We make a histogram of old SC map, new SC map. Old one is black, new one is red. You see Gaussian part and non-Gaussian part. Non-Gaussian part is the essentially SC signal from clusters. And we check the signal level using Planck SC clusters using old SC map and the new SC map. So you see signals are consistent. And also you see we checked a Gaussian part, which is noise with power spectra. And you see a new SC map has a lower noise in entire scale. And we found noise of our new SC map is reduced by 7%. This is an example of SC map of 3 galaxy clusters, this 1, 2, 3. First, we check SC signal with old SC map with 10 arc minute and new SC map with 10 arc minute. They are basically consistent, but we also produce a slightly better, higher angular resolution SC map with 7.5 arc minutes. If you look at the radial profile, black is old SC and the blue is new SC with 10 arc minutes, but red is from 7.5 arc minutes. So if you use this map, you can slightly probe small scales at the core of galaxy clusters. We also check the diffuse gas with 3 merging system in the same way, or the CMAP, new CMAP with 10 arc minutes, they're consistent. But if you use a slightly better angular resolution SCMAP we produced, you can probe more detailed structure here. Okay, now I move from real space to Fourier space for cosmological analysis. I basically follow the same method as Planck 2015 did. In Planck 2015, they cross-correlate Nilk and Milka constructed based on the frequency map of period 1 and period 2. They cross-correlate to not auto spectra because they to avoid a bias induced by the noise if you use auto power spectra. So we made 2 SC maps using half period maps, period 1, period 2, and we made SC map 1, SC map 2, and the cross-correlate, which is red. And you see they are basically consistent, but we have lower noise. It's probably due to lower noise you see in the power spectra before, and also minimal survey stripes. And also we optimize our window function to suppress the residual foreground emissions. Now we use this data and for the cosmological analysis. First, you notice error bar is higher than previous one. This one error bar is only considering the Gaussian part. Now here I include non-Gaussian part, kind of called trispectrum. Now people use this to be precise. Using this data, I model it and fit. In our model of the SC map, there is a SC component plus there's a contamination part. And the SC signal, we consider, we change omega m sigma 8 parameter value, but other parameters are fixed to the Planck CMB result because basically other parameters are insensitive to the SC signal. And also we change B parameter, which is mass bias. We use the Baryon from a Canadian cluster comparison project. It's called CCCP. So it's basically 0.2 with some uncertainty. And the contamination part, there is CAB and infrared source and radio source and noise. We analytically compute this contribution, but of course there is uncertainty. So we use our analytical model as a template and change the amplitude with extra parameters. We fit the data with this model. First, we find this amplitude of contamination part. We all consistent with 0, which means our analytical model for contamination is reasonable. And this is the best fit. Red one is our best fit SC model. And we find SC signal is dominant from large scale to up to angular scale of 6, L of 600. Okay, now we have our best SC model, which is red. We first compare our best SC model with previous Planck analysis from Planck 2015, which is black dashed line, which is consistent. We also compare our result with the ACT and recent SPT result, which is slightly lower than our result, but still consistent within 2 sigma. We finally, we also have a cosmological parameter estimate of sigma 8 and omega matter. you see a slight tension between Planck CMB and lensing from death and the kids. Our estimate is red curve here, which very much consistent with lensing measurement, which is also shown in the S8 parameter here. Finally, we also check the systematic in the parameter value, and we used mass bias prior from CCP, and this is basically roughly b equals 0.2, and we change this prior to different lensing measurement, and also from estimate from hydro simulation. And this is the variation. And we also change pressure profile model. Our fiduciary model used from Planck universal pressure profile from Planck 2015, using the measurement of XM Newton and the Planck. I changed this model to also Arnold 2010 based on XM Newton and simulation, and also change the recent pressure profile model measured with Acton and Planck, and this is a variation. We included this systematic in our final result, and this is the one for the S8 parameter. Now our S8 value is consistent with Planck CME value within 2 sigma. And this is the summary. So I just finish on this slide. Thank you for attention. Yeah.
Okay, thanks, Hideki. There are questions. We have time for 1 or 2 short questions. I have a question regarding the coefficient you found for the other components other than the fit to the Suniata-Davic effect. I lose maybe the frequency where you compute these coefficients.
For the contamination one.
For the contamination, but it is a multi-frequency approach or just a few frequencies, or?
It's multi-frequency approach. For example, for CAB, we compute CAB spectra for each Planck frequency of 6 band, and we combine these CAB components at each frequency with the ILC coefficient used to construct the CMAP.
Mm-hmm. Yeah. So the coefficient you find in the slides are global coefficient that holds at each frequency to rescale this component?
It follows the yes, it follows the coefficient to produce to propagate a C2 frequency map, essentially. Mm-hmm. Yes.
Okay, thank you. There are other questions, or can we move to the next talk? Okay, so thank again. Now we have the presentation by Aurelien about the CMB dipole, the pur si muove.
Yeah, okay. Is that all clear?
Yes.
Am I coming through? Okay, perfect. Yeah, so I'm Raylin. I'm a PhD student at the University of British Columbia, working under the supervision of Douglas Scott. And I'm going to be talking to you today about the CMB dipole and some of the work that I did with Douglas Scott, Dagoberto Contreras, and the Planck collaboration. So if you're looking for the paper that kind of references this work, this is it here. The title is a bit of a mouthful, so it's not one that will attract people to our presentation necessarily, which is why we went with the CMB dipole. But yeah, this is what we're going to be kind of working with. So just on the outline for today. So I'm just going to start by kind of doing a little bit of introduction. Then we're going to just quickly go through the microwave sky and the Cryostat effect, because that will be relevant as we go. The CMB sky and then boosting it, and then dipolar modulated CMB anisotropies to finish with. So let's get into it. So e pur si muove translates to and yet it moves. So it's attributed to Galileo having said it when the church was asking him to recant his claims that the Earth went around the sun and instead of the converse. And kind of the idea behind it is that no matter what you say, you can say whatever you want, the Earth's going to move anyways, and that's kind of some of the principle behind this as well. So the CMB dipole has been measured to very high precision by a range of experiments, including Planck and COBE map. And the simplest interpretation is that it's due to our motion relative to the CMB rest frame. And indeed, if the universe is homogeneous, isotropic, and adiabatic, then this is the explanation for the CMB dipole. But the question is, are there other explanations that could come about? So, there are people who study other theories that could cause portions of the CMB dipole. So, for example, there maybe is a large-scale anomaly like an isocurvature perturbation, maybe varying constants to the universe, maybe some sort of dark energy dipole. So you can see here kind of an example of that. So if I had a cold dark matter isocurvature mode in the early universe, how would that look compared to adiabatic, which is what is kind of assumed to be correct, and also the power spectrum. And many isocurvature models are ruled out by the observations we have already, but that's not to say you couldn't come up with one that would produce some portion of the dipole that we do observe. That being said, often the simplest explanation is the right one. So this is just kind of fun. But yeah, so even though you can come up with these other explanations for the CMB dipole, the simplest one, the one that requires no new physics, nothing beyond lambda CDM, is that the dipole is due to our motion. And so we're going to kind of explore that here, and maybe we'll talk a little bit about whether or not you can distinguish these two effects kind of later on. And by the two effects, I mean a intrinsic dipole that exists in the universe versus a extrinsic dipole due to our motion. Just kind of going into the microwave sky. So many of you have probably seen this before, but the idea is that Planck observes the sky in a bunch of frequency bands, or WMAP or another experiment, Lightbird, whatever. And using these different frequency bands, you can distinguish different foreground effects, model them and remove them so that the underlying CMB sky can be revealed. And all these foreground maps are really useful for other people to study, but also they are between us and the CMB, and so they act as kind of this screen that you have to see through. And if any of these foregrounds happens to have the same frequency dependence, you wouldn't be able to distinguish them from each other using this method. So that'll become kind of important later in this talk, where there'll be two signals that have the same frequency spectrum and so lie in the same map. So in particular, it's going to be the TSZ effect, spoilers. Yeah, so the TSZ effect, as has been mentioned many times, occurs because CMB photons pass through these galaxy clusters. They get an inverse Compton scattering effect. They appear as holes in the low frequency Planck maps, and they change the frequency spectrum of the CMB photons. So we go from having this nice curved frequency for the CMB to being the TSZ effect, and that's shown here. So you can kind of see as it flips through different Planck maps how the different signal looks in each of these frequency bands. And so if you looked at all the frequency channels together and you saw this signal, you'd say, okay, this is a TSZ source. This is how I'm going to model this, and then you could remove it and then try and find the underlying CMB, for example. Yeah. So okay. So we're going to have some equations, but it's fine. We're going to go through them slowly, and I'm gonna talk through all the pieces, and it's going to be fine. So don't panic. So we're going to start with the unboosted sky. So we've got an intensity anisotropes in a particular direction n hat. So Planck maps the whole sky. So each pixel on the sky is some direction n hat. And this is made up of, firstly, the Planck blackbody intensity function, which we're familiar with, hopefully, and the frequency spectrum of thermal fluctuations. So again, this is in relation to a dimensionless frequency x here, but you can just kind of treat it as a frequency that, dimensionless frequency. Just that's what it is. And you get this frequency spectrum, and this is then multiplied with the CMB anisotropes, so delta T over T CMB. And I'm also going to add this other contribution in here. So this is the TSZ contribution. So I didn't write out the full formula for this, but you would have seen it in the previous presentation if you were paying attention, because I didn't want to overwhelm anyone too much. But and multiplied by this YX, which is the frequency spectrum of the Y signal. So that's just down here. The relative frequency spectrum, I should say, because it's I've pulled out this f of x factor here. So this is the unboosted sky. This is just the unboosted sky. We're assuming we're stationary with respect to the CMB here. And it's nice and simple. We've got a component that has a temperature frequency spectrum and a component that has a Y signal frequency spectrum. However, we are on a planet that's going around the sun, it's going around the Milky Way. We're in motion relative to the CMB. So we have to boost this. And so if we're going to boost the CMB sky, it's going to have an effect on all of these parameters. Because with special relativity, we know frequencies will change, temperatures will change, directions will change. And the way this looks is here. Okay, so I know this looks like a mess. We'll go through it step by step, don't worry. So the main thing you want to notice is that mu is the dot product between the direction of the incoming photons and our motion. So it's this cosine theta across the sky. Beta is our speed in units of the speed of light. And then we've got n hat, which was the original direction of the incoming photons, and n hat prime, which is the aberrated or new direction of the incoming photons. And I'm going to ignore the terms that are crossed out, but this is all only to first order in beta. So there are additional terms if you go to second or higher order in beta. So what I've done is I've broken it down into two pieces here. So purple are terms of the frequency spectral, the frequency spectrum of thermal fluctuations. And then we have terms of the frequency spectrum of the Y signal or TSZ effect. And this term here is familiar, should be familiar too. So it's just the CMB dipole from boosting, observed. These are the values, the direction. This is from the N-pipe 100 gigahertz channel. And it's a very nice dipole right across the sky. It's a nice cosine that goes right across the sky. Next, though, we have the other two terms here in the temperature frequency spectrum. So there's the aberration of the anisotropies and the modulation of the anisotropies. So kind of in this graphic over here, what you're seeing is as we're increasing in speed, the anisotropies on the sky will get more condensed in the forward direction and more spread out in the reverse direction. So this is aberration. And the modulation is that in the forward direction, they will be more intense. So cold spots will be colder, hot spots will be hotter. And in the reverse direction, they will be less extreme. And that's what those two terms are in the purple there. And this was actually observed by Planck back in 2013. So Planck 2013 results 27 measured this modulation aberration of the temperature frequency spectrum to 4 sigma. And here you can kind of see some nice figures about, kind of looks a little bit more like a CMB map about how it would look if you were to modulate or aberrate the CMB if we were moving at 85% of the speed of light, which is about 700 times larger than expected. So that's kind of what that looks like. So you can see modulated sky in the forward direction, everything's colder and hotter spots, and then aberration as well has that condensing and spreading effect there. So we looked at this and we said, okay, can we do better? Can we make a better measurement of this effect? Because the way Planck 2013 did it was they looked in the poles and along the equator. But this is an effect that changes smoothly across the entire sky. So can you use the fact that it's changing across the entire sky to make a better measurement? And we said, I think we can. And so if you look at this second half of this equation, which is the Y map signal, you start by just kind of looking at the true TSZ effect. So this Y of n hat is because photons went through a hot galaxy cluster kind of idea, have a specific frequency spectrum that is what we expect to be kind of like, so true kind of in quotations somewhat there. And I'm showing here a map that Milka produced. This is the 2015 Milka map, not the new ones. I didn't know they were there yet, but the map is in YMAP units. So that's those two pieces. So the YMAP has also been aberrated and also been modulated because we're moving. But there's this middle piece here, which you'll notice has no Y dependence. And this I'm going to call the false TSZ effect, and it's the dipolar modulated CMB anisotropy. So it's the CMB anisotropies multiplied by beta mu, which and mu is again this just direction, it's cosine across the sky, and it has the same frequency dependence as this TSZ effect. And I just want to note that the scale bar on this map compared to this map is quite a bit smaller. So I know it looks more extreme, but it's just the scale bar is about 50 times smaller. So this is a smaller effect than the true TSZ effect, which is in this map. So this is hiding behind the true TSZ signal. And it's an independent measure of the CMB dipole, if you can see this, and it's expected to be there. So we expect it to be there because we know we're moving, or we know that there's a dipole that exists, at least in the CMB. And so how to measure it? So the way we did this was we took the TSZ map produced by Planck. We used Milka and a 2D ILC map, and we compared it with 3 directions of modulated TSZ or temperature signals. So we took the temperature anisotropies from Planck, we modulated them in the expected direction and the 2 orthogonal directions, and then we cross-correlate that with the TSZ map. And so if the signal exists in the TSZ map, we expect a signal of 1 and then 0 and 0, or noise for C and D. And we can make a bunch of, so we made 1,000 simulations of universes where there is this modulated signal, and 1,000 simulations where the modulated signal doesn't exist. And we did this comparison with, like I said, the 2 different TSZ maps, and we also used a couple of different CMB maps produced by Planck. And we can see our results here. So just quickly first, the orange histograms are simulations that have no dipole modulation term. The black line represents our universe, and the blue histogram represents simulations with a dipole modulation term. And so as you can see, oh, and then again, yes, thank you. Very quickly, the leftmost plot is with modulation in our expected direction, so the expected direction of the motion. And then the other 2 are in the perpendicular direction. So if we saw a signal in those 2 directions, it would mean that we have the direction of the modulation wrong, or that this analysis isn't working, one of those 2. But as you can see, the universes are consistent with a universe that has a modulation in an expected direction. And we make this detection to 6 sigma. And we do think this method could be even more significant with better Y maps. So it's kind of exciting for me to hear that there are new Y maps on the way as well. And this kind of measurement is also useful to check if the Y maps have been produced correctly. So the signal should exist in there if you've done the Y map analysis correctly, unless for some reason you've removed it. And so it's a good measurement of that. So yeah, so we make this first detection. It's really exciting, and kind of I guess the big question that people have is, can we distinguish a true dipole from an extrinsic dipole using this kind of measurement? Like, is this measurement exclusive to a motion-induced dipole? And unfortunately, the answer is no. So I'm going to go forward just quickly here. So yeah, can we use this measurement to distinguish a true intrinsic dipole from a motion-induced dipole? And the short answer is no. The long answer is math, but essentially the idea is that the signal actually comes about because of a second order expansion of I about TCMB. And so if you take the intensity function that I kind of mentioned early, and you expand it out, you find it turns out that this just naturally leads to a Y signal popping out. And so whether the temperature is including a dipole just from the early universe or including a dipole from motion, this signal comes about either way. So this can't be used to distinguish the 2. But you know, an intrinsic dipole would imply brand new physics beyond the standard model. And though we can't explore it yet using this signal, it's still worth kind of looking to see if there is ever a point where we will be able to distinguish the 2. And yeah, like I said, like it's in here, I think the dipole is cool. You can actually see it in basically every observation you make of the sky is going to be affected by the fact that we're moving. So it's something that, you know, if you're worried about it, you should account for it because it's a real signal that's there. But anyways, I hope that was clear. And if people have any questions, I'm happy to stop now and kind of leave a bit more time as well. So I think Jens has a question.
Thanks, Relin.
Yeah.
Questions, yes. Okay, please.
Carlos, is it okay if I ask?
Yes, yes, absolutely.
Yeah. Thanks for this nice talk. So you mentioned these other terms that appear, which are also derivatives of the Y spectrum, just from the fact, of course, that the Y signal has to be boosted into our frame, that they're small and so on. Have you actually checked if these other terms, also including, for example, an average Y spectrum on the sky, at which level they will provide a noise floor in terms of your error bars? Because I mean, while they might not be necessary to model at the direct, but they would be still at least contributing probably to some error estimates as a floor. So have you checked exactly where these hit? I'm thinking in particular because the null of the Y distortion signal shifts because of these terms, and I'm just wondering if there's any effects that might be important in that respect.
Sure, you're talking about these signals.
Yeah, for example, yeah.
Yeah, so we haven't explored them too much. I think it's something that might be worth looking at, especially now that there's maybe like cleaner Y maps coming out now. Because the Y map, I think, is just a little bit noisier, we didn't look at these terms yet. I actually think that a similar analysis, even to what was done on the similar analysis as Planck 2013, could be done on the Y maps to find these other terms as well. Because this aberration and modulation of the Y maps also hasn't been measured. It should be there, but it would be very difficult to measure just because the Y map is, the temperature map is quite clean, but the Y map comparatively not. But yeah, I think these ones would be interesting to look at, and we're also planning on looking at even higher order in beta just to see if there is any place where further distinctions and further measurements, yeah, it would be interesting. But yeah, we haven't looked at anything in this section of the terms yet. So yeah.
I would have another question, but I'm obviously if anybody else has a question.
Okay, go.
Okay, cool. And here you're showing everything in terms of leading order in beta, of course, and since you're looking at this, in particular, this second red term in the parenthesis, that one is, of course, the modulation term, so very large scales. But do you think there's any real information that one could be looking at much smaller scales where you, in principle, cannot go perturbatively in beta anymore? Or is that all something that is just too much into the direction of like assuming statistical isotropy in the universe and all these things? What do you think?
Yeah, I haven't thought about going to smaller scales so much. We did do this analysis in map space and harmonic space, so you could probably take the harmonic analysis especially to see what happens at the smaller scales. But we also checked to see if this signal had any effect on the bispectrum of the Y map. And as far as we could tell, it has no effect on the bispectrum, so no noticeable, no measurable effect on the bispectrum. So it's quite a small effect. So I think, with incredibly clean Y maps, maybe you could start, trying to do something a little more. But I think just, where we're at right now, it's probably, I don't know if that answered your question.
Great, thank you. Thank you.
Guys, thank you, Reden. And now we proceed with our program. And the next talk is by Sadige about on the Lorentz symmetry violation.
Hello, can you hear me?
Hello, yes.
Oh, okay. So let me share my screen.
Yes.
Oh, sorry, just a minute.
Double time, 2 times.
Yeah. Okay, is it share now?
Okay, great. Thank you.
Okay. Okay. So, excuse me, I have problem by making it full screen, but is it okay now if I go through or?
My screen is large enough, but there is a button, I think, where you can, in your desktop, to move to full screen.
Yeah, just a moment. Sorry.
Oh, I don't see more your presentation.
Yes, just I will
Share again.
Yeah, I'm just.
Please share your screen, otherwise we cannot see.
I think it's again the same.
Okay, okay, we can see. Okay,
maybe.
Please go.
Is it okay
go
now? Okay, okay.
Yes, okay, okay.
Okay, thank you. Okay, thank you. Just because my connection is poor, I prefer to stop the camera and then we'll continue. Okay. Thank you for this opportunity. I am Sadiqeh from Iran. I'm a postdoc researcher in the School of Particle and Accelerator in Iran. I'm going to talk about the impact of the Lorentz symmetry violation on the CMB polarization. Here is my overview. So because of the lack of the time, I just
we are losing it. You
jump it. As you know, the excellent theories in the physics. Physics is a standard model which can explain the electroweak interaction and electromagnetic. The standard model is in good agreement with the experiments till now. However, it cannot explain the gravity. The gravity can explain with general relativity. And there are some theories that bring the standard model and gravity together in a unique theory, such as a string theory. In such theories, Lorentz symmetry can violate in a way that there is some particles known as tachyon. They can get a tensor wave through the spontaneous symmetry breaking, and they can therefore violate the Lorentz symmetry because there is a preferred direction in a tensor field. And also, there are some other theories like quantum gravity and non-commutative spacetime that the Lorentz symmetry can violate in them. And here, there are some the string theory can happen in the Planck scale, in the high energies, but there are some possibility to bring the effect of the Lorentz violation to a study in the low energy, in the available energy, and with a model independent way, which is known as a standard model extension. In a standard model extension, the Lagrangian in the minimum minimum part of the Lagrangian contains the standard model plus some extra sentence from the terms that violate the Lorentz symmetry. These terms contains the standard model field and also some coefficients that that coefficient acts like a background field and produce a preferred direction for an interaction. Therefore, they will have effects on the momentum and energy and the other, the properties of the particles. We look at the QED part of the Lagrangian. A similar a standard model extension Lagrangian, in abbreviation I will call it SME, because we are in this time I'm going to talk about the interaction of the photon, the CMB photon, with the cosmic electrons or baryons. And the baryons is this interaction is similar to Compton interaction, so we use the QED part. In the QED part, you see that this is a Dirac, the usual Dirac equation, which in the gamma part we have the standard model part and also some other fields that some other coefficient that can violate the Lorentz symmetry. As you see, these coefficients have two indices and they are tensor. The C and D here are the dimensionless tensor, and they can have both symmetric and asymmetric components. And the rest are related to the photon interaction that I go through because I don't have time. So there is some constraint on the Lorentz violating term, which all gathered in the paper. You can see from here. This is the archive number, and they go usually update every year. The strongest bound on the Lorentz violating terms are from astrophysics, but there are a lot of experiments that they are constraining the Lorentz violating terms. Our goal is studying the interaction of the CMB photon with the cosmic electrons in presence of the Lorentz violating term, and to see that if this interaction can cause the circular polarization for the CMB photons. As you know, the CMB photons are the leftover radiation from the Big Bang, and nowadays we can measure their spectrum, and the CMB spectrum shows that it is a very good and an exact black body. This black body means that the early universe was in thermal equilibrium. And this equilibrium means that means that nowadays, if we can measure the temperature of the CMB, it is isotropic parameter up to the 10 to the power of 5. But after 10 to the power of 5, we have some anisotropy, which is caused by the some perturbation. In cosmological standard model, it is known that they are because of the scalar perturbation or tensor perturbation. Both of scalar and tensor perturbation can generate circular polarization, can generate linear polarization for the CMB photon. But there isn't any candidate for generate the circular polarization for CMB photons. So if we see any evidence of the circular polarization of the new physics. To study the polarization of the photon, we use the well-known Stokes parameters, which are have 4 components. Here we show that the circular polarization and Q and U denotes the linear polarization. I also shows the intensity. A system of a photon can be described by density matrix, and density matrix components, elements can be described can be related to the Stokes parameter, as you can see here. So in order to obtain the time evolution of the Stokes parameters, we need to use Boltzmann equation. As you see, this is the Boltzmann equation. Left part of the Boltzmann equation contains the effects of the metric, and also any perturbation that is inside the metric. And on the right-hand side of the Boltzmann equation, we have the interaction Hamiltonian. Means that any interaction can come in the right-hand side of this equation. This term, the first term of the right hand, can be related to the amplitude of the scattering. So by using this, we consider the interaction of the photon with an electron in presence of the Lorentz violation, as you see here. We consider 2 components, C and D Lorentz violating coefficient, and the amplitude are similar. And by I jump here, excuse me, and finally we can find the Boltzmann equation if we reproduce the Stokes parameters from the density matrix elements and also obtain the time evolution of them. These are the Boltzmann equation for C parameters, and here in the right hand side you can see the effect of the Lorentz violating term. This K kappa LV shows the effect of the Lorentz violating. As you see, the circular polarization now is a function of the Lorentz violation effect. It means that the linear polarization can convert to the circular polarization for the CMB. And the K parameter is defined here. So by solving these parameter, we can obtain the power spectrum of the circular polarization. The power spectrum of the circular polarization is a function of linear polarization. As you can see here, this is an estimation, is not exact calculation. And if we integrate over the redshift, obtain the average amount of the this value over the redshift, we can estimate the amount of the upper bound on the circular polarization by considering the available constraint on Lorentz violating parameters, which is 10 to the power of minus 15. So the upper bound on the circular polarization can obtain from 0.6 nanokelvin square. And the experimental upper bound on circular polarization is 0.1 microkelvin square. So it is acceptable. And here you can see the ratio of circular polarization to linear polarization in our considered theory. Each color shows the each curve and in different color shows the combination, different combination of Lorentz violating terms. And here, if we consider the ratio of the circular polarization and linear polarization to be of the order of 0.1, it means that the circular polarization should be less than the linear polarization, because as you saw in the Boltzmann equation, the linear polarization can be a source for the circular polarization in presence of the Lorentz violating. So the circular polarization should be less than the linear polarization. We consider this ratio as 0.1, and we obtain the constraint on the combination of the Lorentz violating term. As you can see here, these obtained constraint on the combination are in agreement with the available constraint on the parameters, which is
I cannot hear you longer, Sadia.
which is available now 2 days, and just this on time, in time. Excuse me, I cannot hear you.
Yes, now I cannot hear you. Do you have to conclude, or do you have concluded?
Yeah, as a conclusion, if I have time, I can say just a sentence. Yeah, we show that the circular, in presence of the Lorentz violating effect, scattering of the CMB and the CMB photon which have the linear polarization with the cosmic baryons like electrons can generate circular polarization. And as in the standard model of cosmology, there isn't any scattering that can explain the existence of the circular polarization for the CMB. It means that it shows that this it means that this circular polarization can be related to new physics, that one of the new physics can be Lorentz violating effect. And considering the circular polarization is important because we don't have any background from the standard model part.
Okay, thank you, Sadiga. There are some questions.
Yeah.
Okay, so sorry, the connection unfortunately was not so well, but thank you again to Sadigat.
Oh, thank you. I'm so sorry because now in my country it's night, 9 at night, and I'm at home. Sorry that if the connection was not good.
Okay, thank you. So we continue with Konstantinos about the modification of the gravitation, please.
Yeah, just give me a second. Okay. Okay, you see the slides? Okay, so thank you very much for the invitation to talk to this meeting. It's been a great meeting. So I'm going to talk about new gravitational degrees of freedom as a solution to the dark matter problem. So everyone knows what dark matter is, but very briefly, so dark matter's problem is essentially the mismatch between the observed dynamics of visible matter with its gravitational influence. And we see this, the scale of galaxies, clusters, gravitational lensing, CMB, and large-scale structure. So it's been a very long-standing problem, and there have been many solutions. Most of them revolve around having GR, relativity, as the gravitational theory. And then once we have that assumption, we need to assume the existence of so-called dark matter. And dark matter can come in many different guises. One instance is primordial black holes. It can be a new particle which is not in the standard model, or it can be what we call wave dark matter or coherent fields, for instance, axions. So before continuing to the alternatives, let me discuss a little bit more about what do I mean dark matter, what is dark matter. So regardless of whether dark matter is a particle or wave, doesn't matter, we are dealing with new degrees of freedom, which are in the matter sector. Okay, so we need to add something, some new dynamical degrees of freedom. But cosmologically, we don't need to care so much about what are the microphysics of this new degree of freedom. So if it's a new particle, which can have tons of parameters in the action, as far as particle physics is concerned, cosmologically, we don't really care. What we do care is its statistical description. So we collectively describe the system, we collect particles together, and we assign a distribution function. In the case of wave dark matter, we do something similar. We assume that the wave evolves according to a relativistic Klein-Gordon equation or Schrodinger equation. But in both of these cases, the effective description of dark matter of on cosmological scales is described by the Boltzmann equation. In other words, we have a distribution function which evolves in phase space, and it obeys the Boltzmann equation, and all observables come through the distribution function. So this is what I mean when I talk about dark matter. This is exactly what I mean. So what about other solutions? The only other alternative is that gravity is not described by general relativity when we go to cosmological scales. There's no other way. It's either we have dark matter or we have to change the law of gravity on cosmological scales. So what does it mean to go beyond GR? Because it's not an easy thing to do. First of all, there is a theorem which says that the only local diffeomorphic invariant action in 4 dimensions, which leads to 2nd order field equations, and which only depends on a metric, is a linear combination of the Einstein-Hilbert action with a cosmological constant up to a total derivative. In other words, the only theory which depends on a metric under all of these assumptions is general relativity. There is no other choice, and this is a theory. And of course, all theories have loopholes, and there are ways to go beyond GR, but they all involve into breaking any of these assumptions. So either we have to go into more than 4 dimensions, we can make the theory local, we can break the homomorphism invariance, add additional fields, higher derivatives, etc., etc. But any of these things essentially deal with adding new degrees of freedom. So if we have more than 4 dimensions and we compactify to 4, effective description in 4 dimensions has new degrees of freedom. If we can localize non-local theories, we can restore diffeomorphism invariance, collect higher derivatives by 2. It all boils down to having new degrees of freedom. So in both cases, either whether it's dark matter or new gravitational law, we must have new degrees of freedom. And this is now clear. So the dark matter problem itself means new degrees of freedom. So the question is, what are these new degrees of freedom? And there is one distinction, which is we start from Minkowski metric, and we add a small gravitational perturbation. And then we do the same to the other fields. If the new extra fields, the new degrees of freedom, remain uncoupled from the metric at this level, then we can simply say that these are matter degrees of freedom. So this is what dark matter would be. On the other hand, if there are transformations which mix the components of these different degrees of freedom, simply because we can transform one into the other, then they must be describing the same thing. In other words, they must all be treated as gravitational fields. So this is the distinction I'm making. Of course, once we introduce new degrees of freedom, we have to check that they don't violate constraints on GR. And these constraints are very strong. So deviations are 10 to the minus 4 to 10 to the minus 8 level. But they are on much, much higher curvatures than where dark matter is observed. So in this sense, we are safe, but anytime we propose a new theory, we have to make sure that it passes all of these tests. So now let's get to business. So the motivation behind even considering new degrees of freedom as a solution to the dark matter problem comes back to 1983 by Milgrom. So what he noted was that once you go to very, very small accelerations, that's where the dark matter effects seem to kick in. We're talking about accelerations which are about 1.2 times 10 to the minus 10 meters per second square. And when that happens, he used as a test case the Andromeda galaxy, so which shows us approximately asymptotically flat rotation curves. In that case, if we want to have an approximate constant velocity as you move away from the center, then it means that the acceleration has to fall as 1 over r. And what he proposed that if you change, there are 2 ways to do this, either as a modified inertia, which I will not consider further, but rather if you stick to modifying gravity, the only way to do this is that you change the Poisson equation by including an additional term, which goes as the gradient of the potential, which is the force divided by A naught. So when accelerations become smaller than A naught, then you get a modified Poisson equation, which looks like this. Okay, so that's fine, but there are many, many other observations which we need to check before making progress. So first of all, this has been tested in many other cases. So statistically, what happens is that there is effectively an element of regularity in galaxies. So again, this is a statistical description by grouping galaxies together. Again, when accelerations fall below this A naught value, that's when you start to see the deviations. Okay, so how about gravity? We need to basically have a theory which reproduces this non-relativist description for galaxies, because that is the motivation. But at the same time, we are still able to reproduce correct gravitational lensing, which is not captured by MOND itself. You need some additional ingredient. This is a vector field that Sanders has added to the original MOND theories. You must make sure that gravitational waves travel at the speed of light. Okay, this is in your observations by Van Slyko and Virgo, coupled with electromagnetic counterparts. And then you must make sure you get the correct cosmology. Okay. So what do we have such a theory? So here I'm proposing a very simple relativistic realization of MOND. It comes with 2 additional degrees of freedom, which is a scalar and a time-like vector. This is building on work of others in the past, which introduced these degrees of freedom. This is how the action looks like. It's as simple as it has ever been proposed. First of all, it depends on a metric. It has a new parameter, KB, which was introduced by Bekenstein. It comes to multiplies the action of the vector field, so it has to do with how strongly the vector field interacts. The fact that the metric only appears in the usual Einstein-Hilbert term means that gravitational waves, tensor modes, travel exactly at the speed of light in all situations. So that's taken into account. And then there are some other terms which have to do with the vector. Also important. Very importantly, the vector field has to be unit time-like, and this is something which was introduced by Sanders. And what that does, it introduces a preferred frame. And so once we have a preferred frame, we can expand the gradient of the scalar in a direction which is parallel to the vector, and I call that Q. You can see this here. And on the plane, which is orthogonal to A mu, and that would be the spatial part of the gradient of the scalar. So when you look at the quasi-static situations, that would be like grad phi squared. And then there is a free function in the theory. In all the previous instances of MOND, that has always been the case. So in the absence of a more fundamental theory, I'm going to stick to having this free function. So again, very briefly, what happens on quasi-static regime? You expand the scalar in terms of a new parameter that I call Q naught times T. There is a reason for this, which has to do with cosmology, and I will come to it in a while, plus a perturbation. Also, the metric is expanded in the usual way around Minkowski. It comes with 2 potentials, psi and phi. The vector field, being time-like, means that it's 0 component. It's not free, but it is constrained exactly to have this form, 1 minus psi. Then that means, first of all, on quasi-static scales, this Y term, which is the spatial part of the scalar gradient, that goes as grad phi squared, and Q just becomes a constant, which is Q naught. The function itself reduces to a simpler function, which is just J of Y, nothing to do with MOND yet. That still has to be imposed by assuming a function for J. But the fact that you have a vector, which has exactly this component here, means that through the field equations, you get a constraint, which is that psi equals 5, exactly, in all situations. Which means that if you get a potential, you assume that you have some MOND law, and you get the galaxy profiles correctly and all that you want to have without having dark matter, then automatically the gravitational lensing comes out to be okay. Okay, 5 minutes. Thank you. These are also the field equations in the quasi-static limit. As you see, there is still the free function sitting here. So this is not MOND yet. You have to specify a form for J. But even if you do specify the usual MOND form for J, there is an additional thing which doesn't exist in classic MOND, which is this term here. So this is a mass term, as if the potential becomes massive, if we can say that. And it radically changes the behavior of the gravitational force on very, very large scales. And it is not a free parameter, but it comes out, it depends on the other parameters of the theory. So how does this work? So in the very inner, very, very, very small distances, you need to have a function which tends to just grad phi square times some parameter, lambda s. This can even go all the way to infinity, in which case you have some phenomenon which is called screening, but basically you use to GR on very, very small distances. When you cross some scale here, which depends on m and the new constant A0, that's Milgram's constant, then you switch to the so-called Mondian regime, where forces goes as 1 over r, and the A0 features here in the coefficient. And it's built on that prescription just to fit galaxies. But what is new here is when you cross a new scale, which is given by the inverse mass of this, which appears there, then you get some oscillations divided by some part. And this is something which we have not explored yet. It's under investigation, but it will introduce new features, which are not seen in the standard mode. So these are parameters. And now to cosmology, which is the key point. So cosmologically, the scalar will have some time dependence. It just comes out like that. You assume a free Maron-Welsov Walker metric, that a scale factor is time dependent, scalar is time dependent, and the vector field is just fixed completely because it is time-like, so it plays no dynamical role on exact FRW background. Okay, that means this y is 0. Again, the function reduces to something simpler, this k of q, which has a form of the so-called k-essence theories. And k-essence theories provide energy density to the background in terms of this k. And so what are the possibilities? So for any arbitrary k, you can get basically anything you want, but that's not what we are after. We are after in solving the dark matter problem, and therefore we should be able to fit all the cosmological observations with this phi field by imposing a form on k. Now we know that just from observations that the only possibility that can go if you for this new component is that it has to behave like dust. In other words, it has to have an energy density which goes as 1 over a cube, plus very small corrections, but pretty much it has to go as 1 over a cube. So based on phenomenology, we can ask the question, is there any way we can construct, we can have scalar field which gives dust density in cosmology? And that has been answered a very long time ago. Something called shift symmetric essence or cause condensate model. Essentially, you need to have in the Lagrangian a form which goes as phi square minus a constant. And once you do that, then you automatically get dust density coming out of the theory. Now, because we have a vector field as well, we kind of generalized this case. Sorry.
You have to finish in a
yes,
short time.
Yeah, I'm finishing. I'm going to show some plots. So what happens is that you have the so-called Higgs phase for gravity. The scalar field rose to the minimum and stays there. And so you can expand this function as a Taylor expansion. And this is enough. It's quite general. And once you do that, you get dust density. That's a new parameter which goes into the master. So I'm going to go very quickly here. Essentially, you can solve the field equations. You get draw, which goes as 1 over a cube. You get a time-dependent equation of states, adiabatic speed of sound. And there you go. This is the so-called Higgs phase, where the equation of state goes as 1 over a cube. And in the past, it's completely free, depends on this k of q. Yeah, these some plots with the equation of states. It just tells you that you can actually, some of the functions you can choose are incompatible with the Mond limit, but these are details. But the interesting thing is when you look at perturbations. So what happens is you can take the perturbations to the new fields, you can mix them together, and you can rewrite the equations as something which looks like a fluid with pressure, plus additional fields. And so you have some generalized fluid plus these additional fields which couple to it. But what happens is when the equation state tends to 0, as happens in the Higgs space, then this whole system reduces something which looks like CDM plus some uncoupled field. Exactly. And that's good because that's what will lead to a good CMB. So I have just a few plots to show. So this is what happens to the CMB temperature when you take a standard lambda CDM parameters and change just this KD, just to show that there are some differences happening, which are in fact quite prominent. But once you fiddle with all the other parameters, you can get extremely good fit. So this is, again, Planck data. These are the residuals below. So here I'm showing some models with just different KB, but also changing all the other cosmological parameters so that you get better fits. These are neither best fits, nor have we done any parameter estimation yet, but it's just to show that things can look pretty good. That's a polarization spectrum, also quite similar, and matter power spectrum with SDSS DR7 data superimposed. Okay, so let me conclude. So I have discussed the solution to the dark matter problem, whether it is the usual case of dark matter or whether we can fiddle with the gravitational law. I have briefly discussed the so-called Mond proposal, which implies new gravitational fields. And in the light of this, I have made a distinction: what is a new dark matter degree of freedom field and a new gravitational degree of freedom. Current proposals for Mond require one scalar and one time-like vector. If you collect all the parameters together, in total 5 parameters which can enter the picture, plus one initial condition, which is essentially the dust density cosmologically. And as I have shown, this leads to a theory which has 10 speed equals 1 as required, correct length on galactic scales, correct CMB and matter power spectrum. And then importantly, the same fields which lead to good phenomenology on galaxies also give good cosmology. So I will stop here and you can have questions.
Thank you, Konstantinos. We have time for one single short question. There are questions for Konstantinos? If not, I have a question, which is general. Recently, some people claim to have observed some galaxies apparently without dark matter, and they claim that this is the proof that dark matter exists. What is your feeling about this discovery and opinion?
It's interesting. Question is, yeah. Don't know how much you can say about this. First of all, I have no idea what this theory says about such systems because I haven't studied such systems, so I don't know. But also on the opposite way, the question is how rare are these systems in the case of lambda CDM? So how rare is it to find them in simulations, and why is it that we observed a couple? I don't know if anyone has the answer to this question, but it all comes down. If you have a universe filled with dark matter, then you find systems which don't have them, then you also have to think, why are those things produced in the first place if dark matter is very abundant? So it all comes down to model matter. So it would be good to see if there are many more systems which you find some statistics how rare are these systems.
Okay, thank you. So we move to the next talk now, which is by Mathieu about the tensor to scalar ratio from Planck.
Yes, hi. Can you see my screen in full screen?
Yes.
Okay, thank you. So thanks for the invitation. I will spend the next 15 minutes and we will go from the Mond theory to the constraints on inflation and the result we obtain using the last Planck data. So we already discussed about the Planck data, but I will go a bit more in details for this particular constraints on the tensor modes. So I will not go into the details of the primordial gravitational wave because I think you all know. But the idea here is to put some constraints on the inflation era, which is at the very beginning of the universe history, which will expand the universe very largely and very quick at the very beginning. And the idea is that this expansion phase leaves some imprints into the CMB polarization. And in particular, we expect the primordial gravitational wave produced by inflation to leave some very specific imprints into the CMB polarization, which we call B modes, which are more generally tensor modes, but which one we target into the B modes of the CMB polarization. So the idea here is really to detect something which could be the link between quantum fluctuation and gravity. So this is really an interesting target. So in terms of data for this analysis, we use the last Planck release. We discussed that already a few times, which is called the PR4 and which is from 2020. The so-called name is N-pipe data because this is the name of the pipeline that produces those data. The idea of the improvement is because with Planck we had some detectors which were only sensitive to one polarization direction, and we need to combine those detectors in order to retrieve the polarization signal. And the fact that we combine detectors essentially makes that you can have a lot of intensity to polarization leakage. And due to the fact that the intensity signal is much bigger than the polarization signal in CMB, then you can have some strong bias. And this is a major systematic that happened in Planck data, and especially at large scale where we are targeting the B mode constraints. So why this last release is important? So I said I will not go into the details of all the differences, but just stress on the very important point for this analysis. So I think first, one thing which is important is that this is the first time that the same pipeline has been applied to all Planck frequencies. So it's, in terms of consistency, it's really interesting. Then we have also less noise in the data. So we discussed that earlier. And one thing which is really important as well is that this new release provides us with detector split maps, which can be used to make a really independent cross correlation because detectors are not correlated within each other, whereas the time splits can show up some systematics related to correlated noise, especially at low frequency. So this is really important, especially for those analyses. So here you have an illustration of the improvement of the polarized maps with time. So you have 2015, 2018, and 2020, and you can see that the systematic bias have been largely reduced thanks to the progress of the pipeline. And so this is for the data, but the other part which is new in this PR4 is that those maps are provided with realistic and consistent simulations, and we have 600 of them, which is really complicated to obtain for CMB analysis. This is a lot of CPU time. And those are really consistent in terms of the frequencies, the split maps, and all the processing that have been applied to the real data. So those simulations, they are useful for both things. First, to estimate the transfer function of the processing, so that you can check what you have at the end of your simulation pipeline with respect to what you put at the very beginning, and this defines you how much you affect your targeted signal. But there is also another important aspect of the simulation is that for an instrument which is dominated by systematics, this is the only way to really propagate accurately the uncertainty related to the systematics. So either instrumental systematics or foreground systematics up to the parameters you want to fit, and usually we encode this information into the covariance of the map. So, for example, here you have an illustration of what I just said, which is the spectrum in L domain of the noise in this N-pipe simulation. So, if you in those N-pipe maps, so if you look at the analytical estimate of the noise in red, this is related just to statistical fluctuation from the instrument. And you can see that at very low multiple, we are dominated by another source of noise, which is systematic related, and which dominates the error budget. So this is really thanks to the simulation that we are able to have accurate description of the statistics at very large scales. So for this study, I show you here the difference between the scalar and the tensor fluctuation in power spectra. So in black you have the TT mode, in blue the E modes, and in red the B modes. And in dashed line you have the tensor modes compared to the scalar modes. And the important point here is given the noise level on Planck, which is dominated almost all the signal, even the EE modes at very low multiples. The use of the constraint on EE and BB are really important. So we build a specific likelihood in order to add the information of EE as well as BB in order to fit the constraint on the amplitude of the tensor. So this likelihood is based on an animation-Lewis approximation, which is adapted for cross spectra. I will not enter into the details. You have the paper if you want to go into the specific details of it. What is important is that the idea of this likelihood is that you can transform your space and your variable so that you can get a variable which is more Gaussian, especially at low L, and which for which you can encode the covariance mode by mode using the covariance matrix, which is estimated directly from the simulation. So at the end, this new variable is Gaussian, and you have the statistic of this variable. So the data that we used for this analysis is split in two spectra. There is a very low multiples, which are estimated on the left-hand side here, and you have the E, the B, and the EB modes. And you have the intermediate multiple, I will say, up to 300, where after what we are completely dominated by noise in the Planck regime, which is estimated here. As I said, all the uncertainty are encoded into the covariance matrix, which is directly estimated from the Monte Carlo simulations, and which encode all the systematics, both instrumental and astrophysical residuals. So the results that we obtained are the following. Here we plot just the constraint on the reionization optical depth tau and the tensor to scalar ratio R. For the different modes, so you can see that essentially the reionization is estimated using the E modes, because if I get back to those spectra, you can see that B modes and as well as EB are compatible with 0 in given the Planck noise. But the E mode is sensitive to signal, and this is how we measure tau, and we have some constraints from all modes on R, which are essentially upper limit. They are all consistent with 0. But you can see the improvement when we use the full likelihood, which includes the E modes, the B mode, and the cross correlation between EB. And for the optical depth, we just check that we found a really consistent result with the previous analysis. with a bit lower noise, of course, because we have better data now. So this is the constraint, the summary of the constraint that we obtained on the tensor to scalar ratio R. When we combine also this likelihood in polarization with the TT constraint, so you know that you can constrain the tensor mode using the TT spectra, given the real accuracy that we have with Planck data. This gives almost something like 10% upper limit on the amplitude of the dash line here in the TT spectra. So when you combine that to our likelihood here, you obtain those curves. So the black line is the combination of the TT Planck spectra with the bicep cake data, which is the usual upper limit quoted up to now, which is essentially 6% here. And when we combine only Planck results in red, we obtain something which is really similar with an upper limit at 5.6%. And when we combine both Planck data and bicep cake, we can reduce the upper limit to 4.4%, which is today the best upper limit that we can achieve, given the data. So in conclusion, I will just stress on those new maps and new simulation, which are really interesting. So first, the maps, they are cleaner. I've shown you that directly by eye, we can see that, but also in the spectra. They are less noisy because they contain a bit more data than the previous release. And you have those split maps which allow you to make some cross correlation, which is really useful for CMB analysis currently. And the SIMs, and the importance of the simulation, which are really consistent with the data. So, for example, in contrary to the previous simulation that have been released inside the Planck collaboration, you don't need to rescale a posteriori the simulation to match the noise in the data. They are really completely consistent, and they allow to get as well the transfer function of the analysis and the estimation of the uncertainties, including the systematics. And the result we obtain is really comparable to the bicep cake constraints, but I remind you just that the bicep cake constraints are really focalized on 1% of the sky, going really deeper on 1% of the sky, whereas on Planck we don't have the same sensitivity, but we have a much larger sky, so we are able to estimate the constraint on the tensor to scalar ratio on 50% of the sky, which give also a complementary measurement in terms of sky variation, at least consistency over the sky. And the combined result is quoted back again here at 4.4%. And that's all.
Okay, thank you.
Take any question?
Thank you, Mathieu. There are questions for Mathieu? I don't see question, but I have a question concerning the possibility of using the tools and the methods that you have designed for this analysis, also in the view of the next experiments that will be more sensitive on wide sky areas. Or do you think that some important revision need to be implemented?
But the tools themselves, I think, yes, they are really, they have been developed for that as well. I mean, the likelihood approximation, I think, have been tested with really strong accuracy. So it's a really good approximation for the low L statistic. You know, in particular, you, Carlo, that the low L statistic is really tricky. So this is really a good approximation, I think. And then the idea here is really to focus on the SIMs. So this is really an important part of how to propagate consistently and accurately the residual systematics from the instrument, but also from the astrophysical subtraction. Really, I think for the next generation, here we are using commander maps, so they are cleaned by commander component separation. So really the question for getting lower sensitivity will be not only to reduce the noise statistical noise level and get more sensitive experiment, but also to be able to clean the foregrounds accurately, or as accurate as your noise level, so that you can achieve your target. And for now, we are not able to show that, because given the Planck noise, the only thing we can say is that we are able to clean the data at the level of 4.4% in terms of R, which is not the target of the future experiment, which target more something like 10 to the minus 3. So there is still more than an order of magnitude to gain in terms of foreground subtraction, and this will be the big deal, I think.
Okay, thanks, Mathieu. And now we have the last talk by Laura about strong lensing with sub-millimeter galaxies.
Okay. Can you see the screen? Yes.
Yes, thank you.
Okay, thanks, Carlo. I'm going to show our most recent results about, well, that we have obtained with magnification bias. I'm sure you are familiar with the gravitational lensing, so I'm just going to spend a few words on magnification bias. Basically, when you are observing some distant objects, like those here in the picture, well, what you're going to detect are those sources that have a higher flux density with respect to your detection limits. And they are randomly distributed. Well, you expect them to be randomly distributed in the sky. Now, what might happen is that some of these other sources that have a lower flux might suffer gravitational lensing, and so their flux will be boosted. And this magnification is greater if, well, when the slope of the source number count is large, okay, this beta over here. And then what happened? Well, basically, they might become detectable, and those are the orange sources that you can see here. The key point is in the fact that this excess of sources, well, these extra sources are placed close to the corresponding lens, like you can see here. And this is why we can actually measure this excess of sources. To do this, we use this estimator, which basically compares pairs of sources in the data with pairs of sources in random simulation of foreground and background samples, those here. And so this way you can measure this excess by basically this cross correlation, and then you can compare with the theoretical description. We are using the one by Cryostat 2002, and basically in this description, you have obviously cosmology everywhere, but I want you to focus on the two red terms that you can see here. This term here is important because it's where the astrophysics enters the model. And this is the cross spectrum between galaxies and dark matter distribution. And according to the HALO model, it can be basically it can be split in two parts. You have the one HALO term that describes the correlation between galaxies and dark matter in the same HALO, and the two HALO terms which basically describes the correlation between the different HALOs. As for the HALO description, we are using the HALO occupation distribution, or HOD model, which basically consists, well, you have your HALO, and then you can have a galaxy at the center of the halo if the mass of the halo is larger than this minimum mass that we are going to call M min, okay? And then the rest of the galaxies are called satellite, and an halo can have at least one satellite if its mass is larger than M1. And then the number of the satellites depends on this parameter alpha here. So basically the M min, the M1 and the alpha are the astrophysical parameters that we are looking for. And then the second red term is the term here that I'm sure you're familiar with. And I want just to stress that basically it's here where we are going to put the dependency with redshift of the dark energy related parameters. To do that, we basically write the baryotropic index of dark energy as a constant part here, plus a part that depends on the redshift. And then if you put this into the equation of states for a baryotropic fluid, you basically got that the density evolution is given by this, and it's function of this F here. And the dark energy parameters becomes this one over here. I want just to stress the fact that basically you can get back to lambda CDM if you put omega naught equal to -1 here and omega A equal to 0 here. Well, now, in order to estimate the cross correlation, you need you need to choose a background and a foreground sample. For the background sample, we are using the sub-millimeter galaxies in the Hyrax Catalogue by Herschel, and we are doing this choice basically for three main reasons. The first one is the fact that they have a high redshift distribution, so it makes them a good background sample. They have a steep source number count. They have steep source number counts, which I mean, it means a large beta, and so an increase in the magnification. And the third reason is that they are fairly invisible in the optical band, which basically ensure that you don't mix with the lens sample or vice versa. Okay, so this is why sub-millimeter galaxies are a good background sample for magnification bias studies. As for the results I'm going to present in this talk, we choose as foreground sample galaxies in the gamma survey. The gamma survey is an optical survey with spectroscopic redshift. So as for the area coverage, here in white, you can see the region for the SMGs for the background samples. And since we need overlap with the gamma survey, basically we are left just with the gamma field here and the SGP fields here. And it's we're talking about 200 square degrees of available area. The other important thing in the choice of background foreground samples is the fact that they need to be very well separated in redshift. And for this reason, we choose among the SMGs, we basically choose those galaxies that have redshift between 1.2 and 4 here. And then for the foreground sample, the distribution in blue here, we basically, we analyzed two cases. The first one is a non-tomographic case where we choose galaxies between 0.2 and 0.8 in redshift. And then we analyze a tomographic case where we choose galaxies between 0.1 and 0.8, so a wider range of redshift, and we divided it into 4 different bands that are those, shown here in different blue shadows, okay? So once we have the cross correlation data with this background foreground samples and we have the model, what we're going to do is to basically try to estimate the parameters in the model. And to do this, we use the Markov chain Monte Carlo algorithm. In particular, we are using MCE. And we are going to estimate the astrophysical parameters that are these three parameters here. We are using uniform prior distribution that you can see here for the non-tomographic case. Then for the tomographic case, we are jointly estimating the masses in the four different bands. And then we, as for the cosmological parameter, we are going to, well, we try to estimate the omega m, sigma 8, and h parameter first in the lambda CDM case, and then we basically try to estimate also omega naught and omega a in the case when basically in the first case we allow omega naught to vary, but we fixed omega a to 0, and we are calling in this case omega naught CDM. And then we also run the omega naught omega a CDM model where we allow also for the variation with redshift of the barytropic index. And here you can see the priors for those for these parameters. So these are the results for the non-tomographic case. Here you can see with in blue and red points our cross correlation data, and the solid lines in blue and red are the best fits obtained using the peaks of the one-dimensional posterior distribution of our parameters, which you can see here in this corner plot. The main results for this work are the fact that the astrophysics is robust against cosmology, with respect to cosmology. The fact that we can, basically we obtain lower bound in omega m at 0.24 and an upper bound in sigma 8 at 1. Then we studied the tomographic case, and here in red you can see well, the cross correlation data in the four different bins of redshift. In blue, the blue lines here are the best fits according to, well, for these different cases that we analyzed. And then as for the astrophysical parameters, here you can see the comparison between the masses in the different bins for the different cases, these lines here. And what we can conclude is the fact that the astrophysical results are robust for all the models. Then as for the cosmological parameter, well, basically with the colored lines here are the results for the three cases we ran for the tomographic case, sorry. And what we found is, well, are basically lambda CDM compatible results. In particular for omega m, we have a value of about 0.83. For sigma 8, we got a value of 0.87 here. And well, we couldn't constrain h yet. The solid line, the black solid line here is, well, are the results from the previous case, the non-tomographic one. And so you can see the fact that we actually have an improvement when moving to the tomographic case. This can also be seen here in the sigma 8 omega gamma plane, where basically the dashed line here is the old case, while the colored ones are the results from the tomographic case. Then here are our results about omega naught. Those are basically, these bars are the 68% confidence interval, and well, the red one is our results for the omega naught CDM case. The yellow one is the results for the omega naught omega a CDM case, and well, they are consistent with lambda CDM, where they are basically you have here with the vertical line is the -1 value, okay, and there is also agreement with literature that you can see with the other colors here. Then the last finding is about omega a. We found a value of -0.19 here, and well, which is in agreement with lambda CDM. And if you look at the omega a omega naught plane, you basically, what we got is an anti-correlation that we estimated at about 30%, okay? And this is in agreement with the literature. just as an example, for example, look at this number here. This was obtained with some cosmological analysis with both galaxies, and it has been obtained also combining with Planck and supernova. And just I'm just stressing this because with our results, well, with the results I'm showing you, we are not combining with any other probe. I mean, that's just the results from magnification bias alone. And well, the last thing is that they also find this strong degeneracy in the omega naught, omega A plane. And so here, just to conclude, I want to stress again the fact that the sublimited galaxies are an optimal background for magnification bias studies. And I want to stress the fact that basically with this technique, we have an independent and additional cosmological probe. I mean, well, we are thrilled about that. And we are happy that it's working. I'm aware that maybe the results are not yet so competitive, but I mean, it's just the beginning, and I think it's a good start. And well, as for the results, as I said, we have the astrophysics is robust for all the models. And I want to stress here the fact that I mean, this probe also allows us to basically vary at the same time, to investigate this at the same time, both the astrophysics and the cosmology. Okay. Then the other results we have is the fact that tomography is actually improving the results from the non-tomographic analysis, even if we are basically worsening the statistics. And well, in the overall, we got compatible results with lambda CDM. Thanks for listening, and well, I'm leaving you here some reference about our works on magnification bias. Thanks.
Thank you to Laura. If there are questions, we have time. Okay, there is a question by Hideki.
Yes, just a question about your non-tomographic case and the tomographic case. You see some shift in the cosmological parameter. Did you find some reason for this? Omega M and sigma 8, yeah.
Okay, well, I couldn't explain all the details because of the time. But in between the non-tomographic case and the tomographic case, there have been some other works like some bias studies, bias correction, for example, in here. So, I mean, that's not exactly the same cross-correlation computation, let's say. I don't know if I explain. I mean, there's something, there have been some further studies in between to correct for biases, which might have somehow introduced this kind of shift. I mean, we're always improving.
Okay.
Results. That's I mean, it was actually the non-tomographic case was sort of proof of concept that we made to check if it was actually working as a cosmological probe. And then when we saw that, oh wow, we can do it, so we start looking into the details to see how we can improve and what stuff has to be correct.
Just sorry, one related correction is different in tomographic case and a non-tomographic case. Is this what you said?
We have slight bias, some sort of biases correction. You can find the details over here, and those are slight correction. If I recall correctly, they are mostly affecting the larger scales. And but yes, there have been applied some different correction in the second results.
Okay, I see. Yeah, okay.
You can. I mean, you can check the paper for if you want all the details. Okay.
Okay. Thank you.
Okay, thanks to Laura. You have a question regarding the comparison between model and observation and the samples that you have selected. From the theory, I understand that if I well understand, of course, that you have implemented the model, including the Halo model.
Okay, it was at the beginning, right?
Yes, in the beginning, yes. And
yes,
then,
that's the yellow, yeah, this one, right?
Yes, then you apply the method to the comparison with the data from samples of galaxies. So in this respect, I asked to you if with this model, for the Halo model, you tend to monitor both galaxy and galaxy lensing and correlation, or also cluster of galaxies may act like a lens with respect to your different objects, which is a paper that I see to be submitted, maybe by Fernandez. I don't know if there is something that is regarding this topic.
Yeah, I mean, you're asking that's, I mean, if you want all the details of all the stuff that enters the model, it's basically the model, this one from this reference here, and where basically you are taking into account almost everything. I think the only difference we expect to the already published paper with the new results is in the fact that, well, we are splitting with for the two-sided tomography, let's say, and the fact that we are also well investigating the possibility of variation with redshift of the let's say dark energy related parameter. And so, but it's I mean, the model is this one, and yes, you have to take into account everything.
Okay.
I don't know if it was
okay. And in the data, essentially, you have galaxy and galaxy, like foreground and
in the this one in the estimator, you say?
Yes, in the estimator, or everything is included, also galaxy cluster also in the estimators.
No, the estimators are, well, the simulation are made in order to be I mean to take into account the characteristic of the true samples. But you don't want to take into account lensing, because I mean, here the key is the fact that you want to measure the excess. So you have your catalogs, and you will have some extra correlation, which is due to the magnification bias. Okay. On the other side, what you want to know what will be the signal without the lensing, right? And then this way you can measure the excess in the data.
Okay. Thank you.
Okay.
Okay.
Right.
Yes. Okay. If there are other questions to Laura or to other speakers of today, we have 5 minutes, and then the session will be automatically closed. So, Jens, maybe do you have a question for Amanda? If Amanda is still there, but I don't know.
No.
Okay. Okay. So it is a pleasure to have all of you, and thanks to our speaker for the very nice presentation. And so stay tuned with me and with the organizer for the preparation of the proceedings, which is, I think, an important part of this conference. And okay, so the conference will continue, and I in particular recommend the other session related to the cosmic backgrounds. Of course, Jens is here, and we will lead the two of the next session, interesting for us, I think, but there are other sessions that are very interesting. So enjoy the conference, and thanks to everybody.
Thanks, Carlo, as well, for this nice organizing and putting together this nice session. And yes, just to echo Carlo as well, would be great if to see many of you tomorrow as well in the morning session on New Horizons with spectral distortions. Thank you. Yeah.
Okay. Yeah. Thanks to everybody. Bye.
Thanks, everyone.
Thank
Bye.
you, everyone.
Bye.
Bye-bye.
Bye.
Bye-bye.